session. Just checking if there is somebody outside. No, no more people. This session is devoted to specifically to reverberation mapping, and the first speaker of the session is Andjelka Kovacevic, who will tell us about photometric reverberation issues and consequences.
Thank you so very much, Professor Bozena. It is a great honor to be in this session together of all experts from various fields of the AGN community, and our special thanks to Claudia Reitieri, the leader of our big brother Italian in-kind contribution team, for giving us opportunity to present some key points, exercises from our interactions through various conferences and collaborations with Angela Boggiorno, Demetrio Di Chicco, Vincenzo Petreca, Maurizio Paolillo, and all people from the AGN and TVS community in relation also with IPS office. These simple exercises points are actually will be given under the code of conduct of the Vera Rubin Observatory, and under the efforts of democratization and empowering people to do the science. During these wonderful days that we are enjoying, we have some key points. There are many, many key points, but during this talk, I will actually connect to the characteristics of the AGN as a key example of LSST, non-static science, connected to the efficiency. And we have heard about importance of the efficiency from the follow-up, from the operation on the computing machines, but what's more important, we also had points from Mara, Salvato, and Paolillo about the distribution on the efforts from various scientific software points. And today we will have at the Rubin community workshop important discussion how to measure efficiency of our science during the Rubin operations in response to the climate changes, weather uncertainties, and what's more important, to the very fast varying scientific landscape. And we will give an early example how we as a community had a challenge from the broader astronomical community to respond to what is happening actually with other large surveys. And we will present this immediately. And as non-static science, we like it or not, we are operating under the Nyquist theorem, which means that actually the our scientific output will be strongly constrained by the uncertainties of our signal determinations. Either these are periodicity, time lags, structure function, signal, or whatever. So, and we will present simple exercise by beautiful metric constructed by RED scientific team. We have heard about this survey from Bestock yesterday. And also, I'm sorry, we will just, in order, we have seen during the conference that we are already responding to the reconfiguration within the AI machine learning landscape, and we have seen all of these beautiful talks and examples. And what will be important, how we can make the corridors between these very, how to say, important branches of the hard scientific reasoning. And my personal vision will be actually that we go to something which will be LSST AGN astronomer large language model at the end of the 10 years of the operations. And we are seeing this at the link talk. I recommend wholeheartedly to the young researchers to listen to this AI language model talk given by Joe Kuka, and they are already going into something that will be actually new colleague astronomer. So in order that we are actually going to something which will be large, a language model, we should step uh, uh, back and take a look into already existing tools from more broader mathematical perspective. And here will be given some simple early examples of this, how to take a look into already maybe old fashioned tools, but from the broader mathematical perspective in order that we go into something which will be a large LST AGN language model after the 10 years of the preparations. And we will hear during this talk that we will actually operate during these 10 years at various asymptotic regimes of the emission of the accretion disks. And during this morning and afternoon session, we will hear about many problems related to the contaminants from the dust in the overlapping region of the photometric reverberation mapping, then continuum reverberation mapping in the talks by Secunda and Lee. And this actually is really important that we know that our methodologies should be will be actually in various asymptotic regimes. From the other side, during these days, we have explored the main support of the AGN parametric phase space related to the masses, accretion rates, really important, given by Maurizio and Andjelka. But what is actually what is challenging is relativistic parameters, because as we can see, Scherian plates is subtle parametric regimes. They are actually not so nicely connected, and that is something that we should navigate during this 10 years. Also, we can see here from the perspective of the continuum reverberation mapping, the main tasks, mostly exploration is done in this main axis, supporting the spanning the whole parametric space, and once again emphasize on the geometry and relativistic parameters. See some examples, some related to this relativistic parameters and their importance. Also, as for the continuum reverberation mapping, there are a lot of exploration related to the transfer function, and once again, we have need, for the relativistic parameter exploration, and we have heard something really nice from these talks, and especially from the early career scientist Fagin yesterday. And still, our photometric reverberation mapping is in industrial scale is challenged by the problem how to disentangle the continuum information, the emission line, and we still need some information coming from the spectroscopy, and that actually that will be given by Professor Czerny, Lira, and Panda today. However, this is also not only the challenge, but also the possibility that we exercise some other techniques for disentangling the information, and we will talk about this. And there are two rails. We will be railed between these two important uh, 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 how to say, axis, and we have heard about a really nice investigation given by Maurizio and Vincenzo related to the accretion rate, and then once again we can operate our algorithms, methodologies under various types of the asymptotic behavior. From the other side, we have heard yesterday that for example, from the talks of Rolf and Best, that we are actually examining the configurations of the theoretical and the observables parameters we can infer. And if we take a look in the standard configuration for the accretion disk and take a look into the eigenvalues, we can see actually superposition of the quasi-periodic information on the top of possible chaotic behavior, and then we have one axis related to the more to the neutral stability. This is also one example of the exercise that we will take a look during this talk to see how we can use it for some relativistic challenges. So we will see how we can respond some prototypes of the changes within the landscape on the fly of the LSST, and the first will be related to AGN science collaboration publication from the 2022. Then my personal opinion that blazars will be really great game changers, and maybe new possibilities from the QPOs. Okay, as for this problem, in 2022, we have been asked by a reviewer coming from the broader astronomical community how we are actually sure as the AGN community that we will not have actually or we will have relativistic effects during the reverberation mapping and determination of the time lapse. Using Campotiello curve model, we actually shown here that standard Shakura model and relativistic model of the accretion disk for the rotator of about 80% are almost asymptotically similar for the angle used below 20 degrees, less rapid rotators below 80% have almost similar pattern to the standard model, and extreme we can expect for the ultra rapid rotators close to 1. And then we actually shown this ratio between the relativistic time lags and the normal time lags that will be seen after the 6 gravitational radii as we are going down to the plunge section of the supermassive black hole. That is the simple example how to respond on the fly to the relativistic effects. From the other side, blazars as really important the connection with the black holes, and here is really important study of the blazars from the side of the LSST. It is possible actually to use them in order to infer the actually the spin of the black hole, but I am not going now. It is demonstrated in this study. And from the other side, we can use QPOs because they are naturally superimposed on the chaotic behavior of the accretion disk to try to probe linear relation from stellar over the intermediate up to the super massive black holes in order to try to constrain the spin. And here is some simple exercise. Okay. And then we, in order to measure the efficiency of the algorithms, we have been applied the we have been used the metric from the red hole, and you can see here their investigation of the, for example, of the javelin, because of the many construction. This algorithm will be actually efficient in the certain saturated region below 170 days, according to their studies, and there is a certificate of variance in combination of these methodologies. And also we apply this for the LST and the metric, and what we found is actually that as much as we have the smaller affinity below, much below 50%, we will have higher efficiency. The next is actually that we are having for the continuum lags, as we are going from the G to Z band, that actually efficiency is going down. And from the other side, accessing the Shen 2024 calculations and repository, we found that algorithmic efficiency for the CF javelin and Pyra is actually non-linear in response to the distance from the supermassive black hole, where we have actually increasing variability in the opposite direction. And we can actually see certification of all time lags that we have well somewhere around the region H beta, H alpha, and also even using their recommended lags. And we can saturate all of this information that maybe we have something here overlapping of the complexity here closer to the black hole, maybe signal is still stronger, while here further away we have something that is more pronounced and then suitable for the algorithms. From the other side, they use also and produce the time lags from the using the PyZDCF code made by our PhD student Isidora Yankel, and you can see here actually how it looks like by SCCF and composite for all objects in the study of the Chen 2024. And it is important to see that PyECCF is like the distribution or the filter detecting signal on the long range at the time by that. PyECCF is the filter more pronounced, more sensitive to the variation with the light curves. And that was for all emission lines. From the uncharted territories and also going step back, we can see here an example from the Vera and beautiful methodology to disentangle accretion disk, SAD, SED. And if we take a look into this equation, it is nothing else than constructing the tensorial field from the wavelength and time. Here is the bias, and then it looks like like the neuron as well from the, and we can construct some simple exercise to try to extract the SED using machine learning. And for this, we are using the and first result looks promising. From the other side, we know that for the reverberation mapping, we can also use this methodology of disentangling cross-correlation function between the bands and the autocorrelation. But what is also we have produced this notebook for the community, and it is in repository of the NOIR lab. But here is we are presenting the simple autoencoder and the regressor connected by the corridor of the latent space, and our attempt to disentangle continuum and the emission line from the total simulated light with a very fast cadence corresponding to the level of the H alpha. But you can see that everything could work until a very low percentage, where we have more pronounced departure from the real signal. You have seen yesterday our work on recovering the transfer function and recovering the characterization of the variability. From the end, here is some simple promising results from the quantum neural processes. And this is my, how to say, final thought, that actually in order that we detect signals, we are actually we are constrained by Alan Turing postulates of the computing and the Gödel two incomplete theorem, which means in our science that we can build the algorithms, but these algorithms perhaps will not work for the all objects. And in order to overcome this, we need more heuristic and holistic approach of the combination of the methodologies. So thank you so much.
Thank you. We have time for a few questions. No questions? Oh,
Thank you, Andjelka. And I think at the last slide you mentioned the quantum. And
Yes.
can you say a bit more about that? I didn't have time to see.
Yes, this is actually the exercise with our IT students, and as I already said, the mission is actually to empower the young people, specifically women, and we have 3 students from the IT department, and the quantum neural process is actually we are running this on the circuit on the Google machine, and it's actually consisting of the 4 qubits. The depth is about 8, the star-like composing system, and actually we are actually building the latent space using, because we can use entanglement states and explore much broader, how to say, possibilities of the combination of the input parameters. This is the prototype, looks promising. On constructed, we are using actually one of the light curves simulated by Aman. You can see it is very fast cadence, about 1 lower, maybe half day, and it looks promising. We have confidence bands that are now okay, but we should explore more these, and this is something that is already doing the community, and I would recommend the talk by Matthew Graham during the ESO conference, synergy between the LSST and the ESO facilities, held this January, where he also presented with his colleagues the quantum neural network for the classification, I think, images or something like this, and they have already talked about this. So the quantum processes are coming, and we are actually grateful that we can do this with the IT students.
unless somebody has a very short question. Okay, so let's thank the speaker. Thank you, Andjelka. And now we move to the talk by Amy. Secunda, which will be on reverberation mapping of accretion disks.
Awesome. So while we get the slide set up, I kind of work on two different things that I am very excited about Rubin for. So I'm going to try and really briefly touch on both of these, but I'd really like to talk about each more. So if you have any questions or thoughts or anything, please come talk to me. Okay, so I just want to start by saying that I think now is an absolutely amazing time for reverberation mapping science for two main reasons that I'm going to talk about. So the first is that we now have these multi-wavelength radiation magnetohydrodynamic or MHD codes. And the second is the reason we're all here today, and that's because of Vera Rubin Observatory. So first I'm going to talk about multi-wavelength radiation MHD codes. And before I even go into any more detail, I'm going to talk about what this does and what it doesn't do. So what it doesn't do is what a lot of the really nice models we saw yesterday, and I think we're going to keep hearing about today, that we can use to train machine learning methods on. So it's very computationally expensive. It doesn't focus on, what is the angle of the incident X-ray photons. It doesn't focus on what are the GR effects. It doesn't focus on what is the radial temperature profile of the disk, although we can look at how X-ray photons might change the effective temperature of these disks. What it does is it specifically focuses on how do you put in X-ray light curves and get UV light curves out. What does the gas do to that? And how does the gas do this reprocessing? And I want to thank Patricia yesterday for talking about intrinsic variability, because it also lets us study how do fluctuations in the AGN disk impact the UV or optical light curves that they emit. So, okay, I'll show you really quickly. These are the main equations that we evolve in our simulations, right? And each part is important. So the hydrodynamic part is very important, right? This is how we evolve the gas, the density, the momentum, the pressure, the energy of the gas. The next part is the magnetic part, which is also very important, right? It's important to include magnetic fields. We think that the magnetorotational instability, which is driven by the magnetic fields, is the main driver of accretion in AGN disks. So very important to include. Next, we have the radiation. So in these simulations, we couple a radiative transfer to the magnetohydrodynamic evolution so that the radiative transfer depends on the properties of the gas, and the properties of the gas are impacted by the radiation. And we do that through adding these two source terms so that I have on the right-hand side of the second and third equation for the radiation pressure and the radiation energy. This is important because we think the inner regions of AGN disks are supported by radiation pressure. And also because, again, if I'm trying to track how this radiation changes by the disk, we really want to make sure that we're being self-consistent in the way that we solve these. And then finally, this is the really novel thing that makes me really excited about these simulations is the multi-wavelength part, right, which is represented in these summations here. And what that means is, right, if we want to look at how X-ray is reprocessed into UV or optical by the disk, we're going to need at least two wavelength groups, right? A short wavelength high energy group for the X-ray, and then a longer wavelength group for the local black body radiation. And so that's what we do, right? So I simulate a small region of the AGN disk. And first I have one, radiation wavelength group that represents the local black body temperature. So in this case, it's actually UV for this region of the disk. And then I take an X-ray light curve, which I model for the simulations you're going to see today as a damp random walk. And I inject it into the simulation as if it's coming from the corona as a second wavelength group. And then finally, I can measure the UV light curve coming out of this simulation. So I'm going to skip right to the latest results. If you're familiar with my really recent 2024 paper, I'll say the key upgrade here is that we've upgraded how we model the opacity for the X-ray radiation by adding, by using tabulated opacities, which add line opacities and increase the absorption in our simulations, which gives us, as a result, some really well correlated injected X-ray and reprocessed UV light curves. We find a Pearson R coefficient between the two light curves of 0.92. So again, the gray is the X-ray that we model and inject into the simulation, and the purple is the reprocessed UV that the gas re-emits out. And so now that we have these really nicely correlated light curves, we want to say, what is the transfer function for the reprocessing in our simulations? And because we have these even cadence light curves from our simulation, it's very easy to Fourier transform them and use this simple equation to calculate our transfer function. So the purple points here are the transfer function that we calculate based on our simulation data. And the gray line here is our best fit Gaussian model for the transfer function that we fit to this data. A Gaussian model is somewhat standard to use for this transfer function. And we find that it's a good fit in this case. So here in gray, I'm showing our forward model UV light curve based on this best fit response function. So what we do is we take the X-ray light curve, we inject in, we reprocess it with the best fit Gaussian transfer function, and then we look at the PSD in gray, and we compare it to the PSD in purple, which is the PSD of the actual reprocessed light curve from our simulation. And you can see they're a pretty good match. The fractional error I'm plotting in the bottom plot is pretty close to zero and doesn't show any real significant trend. So great. So in this case, the Gaussian transfer function is a good fit to our data. But we do another simulation where all we do, we take the same injected X-ray light curve and we only inject a quarter of the flux, of the X-ray flux. And now all of a sudden, you don't have super well correlated X-ray and reprocessed UV light curves, which you can both see and see in the Pearson R coefficient of 0.22. And when we look at the transfer function and we try and fit a Gaussian, you can already see these points are not well fit by a Gaussian. And when we look at what's been forward modeled, right, the reprocessed UV light curve we form using our model significantly underpredicts the actual variability in the UV, in the reprocessed UV light curve from our simulation, right, at these low frequencies, right? This is just an underprediction by our model of the variability. And the reason for this, we can see by looking at the actual PSD of our various light curves. So in gray, we have the PSD of the X-ray light curve we inject into the simulation. In purple, we have this same PSD for the reprocessed UV light curve. And in navy, we actually have the PSD from our intrinsic UV light curve, which we get by running one simulation where we inject no X-rays and we just look at the UV emission. And first, right, you can very obviously see that there's a lot of intrinsic variability in the UV light curve, right? So even if there's no X-rays to be reprocessed, there's still going to be variability in your UV light curve. And then also you can see that at low frequencies, this UV variability, there's more at low frequencies, long time scales than in the X-ray. And so using just, a Gaussian or even a linear transfer function to model this reprocessing is difficult because it's never going to capture this low frequency variability because it just doesn't exist in the X-ray light curve. Okay. So just a brief summary, right? The fluctuations in the AGN disk lead to intrinsic variability in UV light curves emitted by the disk. The level of X-ray reprocessing we found in these new simulations is very sensitive to your opacity model for the X-ray photon. So that's something to pay close attention to. And then in some cases, the Gaussian transfer function is a good fit, but in other cases, it's not clear if even a linear reprocessing model is going to be sufficient. So, okay, so I'll move on to the second part, and that has to do with kind of the science case that I'm excited about for the Vera Rubin Observatory. And that's the long negative lag. So the long negative lag, right, I've just showed that we think that fluctuations in the AGN disk, maybe from the magnetorotational instability, maybe from convection, lead to variability in light curves emitted by that region of the disk. So let's say that you have some fluctuation in an outer cooler region of the disk. Well, that'll impact the variability in that light curve emitted at longer wavelengths. Then over an inflow time scale, that perturbation will get accreted inwards to the inner region of the disk where it's hotter, and then it'll impact the variability emitted at shorter wavelengths. And so we can, just like we do with continuum reverberation mapping, measure this lag. We call it long because the inflow time scale is much longer. We call it negative because it goes from, you see variability first in the long wavelengths and then the short wavelengths, which is the opposite of traditional continuum reverberation mapping. And what's really exciting about this is that the inflow time scale depends on the height of the disk. The inflow time scale depends on the height of the disk. And so we can use these long negative lags, if we can detect them, to learn about the vertical structure of the disk. And the reason I'm excited for LSST is because it's going to have that long baseline. Okay, we actually think we detected one of these long negative lags. I think I've shown this plot, talked about this detection before in Feral 9, but just really quickly, here I show the lag as a function of wavelength detected between these wavelengths and our reference waveband. And we fit this model here shown in green, which tells us that the height of the disk goes as the radius to the 3.6 power, which means we have really dramatic disk flaring in this region of the disk. And so what's new is in the last few months, I've been working with ZTF light curves to try and detect more of these. So far, I have 7 potential candidate long negative lag detections between the G and I band primarily. And I'll show you really quickly the results. Here are the Javelin distributions for one of these potential long negative lag detections. You can see a peak in the Javelin distribution for the lag between the G and the I band at around minus 230 days, and between the G and the R band around minus 140 days. And so this is actually a pretty robust Javelin detection for us for a long negative lag. We haven't talked too much about Fourier methods to use to detect reverberation mapping lags yet so far, but these are really useful for us because it lets you look at the lag as a function of frequency, which makes it easier to isolate the long negative lag if you also have your discontinuum lags. And you can see I used kind of 2 different methods to deal with the fact that we have uneven cadence light curves. And so one is this maximum likelihood method, and one is one where I just linearly interpolate the light curves. Very simple. But you can see in both cases, the G to I band lags detected by these Fourier methods are very similar to the lag shown as the horizontal blue line detected by Javelin. We don't get anything for G to R, but it's still kind of unclear if that narrow wavelength range you can detect a long negative lag for. So the G to I band lags are really promising for these because all 3 methods that we use find a similar long negative lag. Really quickly, I can just show you the results from our Mach light curves. We make 100 Mach light curves where we use the cadence from ZTF, and we inject a long lag only, I guess, on your left, and then a long lag and a discontinuum lag on the right. And here I'm just showing the fractional error. The mean is the dot, and the error bars are the standard deviation. Just one thing to note here is that this very simple linear interpolation Fourier method seems to do the best on our mocks, right? It's reasonably accurate, and the standard deviation of what it detects is not crazy broad like the maximum likelihood Fourier method. So going forward, this is something to keep in mind for me, is that that's a good method. But I'm also very much on the market for new methods for detecting long negative lag. So excited to keep talking to people here about that. And then just finally, I'll just show this plot where I show the long negative lag we predict based on the mass and Eddington ratio of these AGN, which are the most important AGN properties for setting the long negative lag duration. And then I'm showing on here the 7 potential lag detections that we have. And this is for a model where the aspect ratio is 0.4, which is very thick, right? But it's at this aspect ratio that we find lags that are similar for these 7 objects to what we're actually detecting in the data, which is roughly hundreds of day lags. And so so far, these preliminary results, again, suggest the presence of a really thick disk in the optical region. And right, I'll skip this slide because I think I'm out of time. But all I'm saying here is we've done these mocks for LSST mock light curves. And you can see here in the diamonds are the Fourier method and the circles are javelin, and we're doing it for 3 different lags. It's a lot more accurate for our mocks. We detect long lags a lot more accurately in our LSST mocks. So that's really promising that anything we develop for ZTF is going to work even better on LSST. So that's exciting. Yes. And so just in summary, really interested in these long negative lags. They're predicting more interesting vertical disk structures than, the standard thin disk model. And they're really useful way to test the standard thin disk model if we can detect more of these. Okay. Thanks so much.
Okay. Thank you. Extremely important results. Okay.
So thank you, Amy, for this nice talk. It's very impressive work. I wanted to ask about how do you generate the intrinsic variability in your simulations? So that's my question, but also some comments. So in my youth, when I was doing this stuff, we postulated the same thing based on data that you couldn't reproduce the lags and the relative amplitude of variability only with reprocessing that on long times because it was needed to have. So it's great that this is actually panning out. And yeah, so my question, how do you do it?
Yeah, I'm very familiar with that work. Yeah, we're excited to be finding similar things. I didn't really, we've also been fitting random walk models to the PSDs of our various light curves and seeing some things that agree with observations. And so I'm happy to talk more about that at a later point. But for the intrinsic variability, so again, we have this one simulation we run where we don't inject any X-rays, and all we do is evolve the gas physics and see what UV flux leaves our simulation box, right? And that's how we generate this light curve. We just plot the flux as a function of time. And so looking at the physics that we see inside our simulations, we see that we're driving MRI turbulence. And we also see that we have some inverted entropy profiles, which suggest that we're driving convection. And so it seems to be some combination of the two is what's driving this intrinsic variability. But that's something we also want to look into for specifically which it is and in what measure. So
Okay. Can you come back to your javelin results?
yes, absolutely.
One question about
Yes.
this. So this is too similar to the values of the gaps in the data. Have you checked if you're not just measuring the gaps?
Absolutely. Yes, that's a great question. And so when we actually, we have a whole bunch of criteria for selecting out the potential detections. And one is that it excludes the gap for the G to I band lag. We're mostly focused right now on G to I because again, the G to R picture, we don't know how over what radial scales these perturbations are correlated. So G to I just feels very G to R feels very close. But for G to I, we just require it to be the peak in the lag to be, I believe, over 220 days. To essentially not be between minus 220 and minus 160, which is when we do mocks of these where we do null tests where we don't inject any lag and they're just light curves. That's where we find that javelin between minus 160 and minus 220. And so we don't even look at any javelin distributions that peak there, because at this point, we can't say that it's not just a signal from the gap. So we think that this peak is at a long enough duration that it isn't a signal from.
One last question.
Hi, I was wondering, in your simulations where you assess the intrinsic variability and the reprocessed use variability, but don't you expect the disk to feed the corona and so have a loop, like a loop that would sort of smear out your correlations?
Yeah, absolutely. So at this stage, we're simulating like a small chunk of the disk. And so we're not really able to look at, right, like how this intrinsic variability gets accreted all the way inward, impacts the corona. So we're not really able to look at the feedback loop right now. And so we're kind of just doing the isolated view of how does, an uncorrelated X-ray light curve get reprocessed. But yeah, that in the future, it's important to look at that feedback loop, and that's something that we hope to actually, be able to look at with the long negative lag as well, because it's specifically, tracking that.
Let's thank the speaker again. And now we move to the third talk by James Chan, which will be again about the properties of accretion disks, as revealed in the reverberation model.
Hello? Can you hear me? Okay, great. Hi, I'm James Chan, postdoc working at the City University of New York and the American Museum of Natural History. So thanks so much for giving me the opportunity to share my work with you about the accretion disk model. And this work also work with Josh Fagan and Henry Based. So basically, my work is a little more related to theory. So I would say it's like progenitor of the from Josh and Henry. So we know that the thin disk and the lamppost model may not be the truth, but because it's very simple and also easy to use, so I think it's worth to still explore these two models and extend them a little bit. And so that in the future, since now we are the era of the big data from the LSST, so I think it's also very important if you want to use machine learning to have a general model for the accretion disk to simulate the light curve for the LSST. Okay, so this is a very simple cartoon to describe the thin disk model and the lamppost model. So we know that there's a black hole at the center and surrounded by the accretion disk. So the light coming from the corona will reprocess and re-emit from the disk. That's what we observe in the different wavelengths. So basically, we can describe the temperature of the disk with these two terms. One is viscous heating, one is irradiated by the lamppost. So the time variable term is coming from this part. Okay, so I know there are so many parameters, but let me just describe it very quickly. So now you can see there's a height of the corona, and also the Rin is the ISCO, and which is determined by the spin. And also there's another parameter is the outer limit of the radius of the disk. So based on the temperature slope, you can calculate the, assuming the accretion disk is a parabotic radiation. So then you can put it in the formula, and assuming the temperatures fluctuation is very small, you can decompose these two into the time dependent term and the time variable term. And also the flux can do the same thing. So when the temperature fluctuation is very small, we can approximate the light curve as like transfer function involved with input variability. Okay, so in this model, in this work, we try to extend the disk model. So for the accretion rate in our work, we try to use the simple model, use the power law. So now the accretion rate is not a constant. It follows power law and it's motivated by kind of the wind model. So yes, as I said, there are so many parameters, but in this talk, I will just focus on these two parameters. One is the beta, which is the power index of the rate. Another is the color correction factor, which is we put it in the Brabant radiation. Okay, and other nuanced parameter I will list here. And in this talk, I will also limit it my my parameter space for example, the speed of the black hole is assuming to be 0. So that's why you see the east cone size is 6 times the gravitational radius, and the height of the corona we assuming very small. It's like a 12 RG. But of course, this is the talk I present here. I limit it to that. But in our work, we explore quite wide parameter space. So first, I want to see the impact of the wavelength. So here you can see the light curve, simulated light curve. And the white one is intrinsic variability coming from the corona, and the color curve is like blue one, and the orange one is coming from the integration, directly integration. But here, in fact, I also have the dot line and they overlap. So that means the this is calculated from the convolution method, like approximate method. So because in this case, the temperature fluctuation is quite small, so the convolution approximation works very well. Okay, and then here I want to highlight something. These two lines. So here you can see the shape of transfer function, and the mean of the transfer function corresponding to the shift of the light curve. And most in the literature, sometimes people confuse which one they should use, how to calculate that. But here we really check. The correct one we should use is a kind of variable term of the probability radiation, which is the derivative of the probability radiation. Yeah, so that you can have the exact self-consistent time lag. Okay, then let's see the impact of the power index on the accretion rate. So of course you can imagine if you increase the power index, you will change the slope of the temperature, so temperature profile. So if you increase the beta, you will make the temperature slope shallower, and that would also make your time lag a bit longer. And now let's see the spectrum. So here you can see the time lag spectrum and the luminosity spectrum with the wavelength. So here you can see that if you increase the increase the beta, that would change the slope, the relation between the time lag and the wavelength. That can also kind of mitigate why the disk size is a bit larger from the observation, because usually if you use a traditional disk model, it can be too small. But if you include this term, this beta, which means you can change the temperature slope, you can mitigate this problem, and also the luminosity can be also enhanced. And here you can see the dot line. So the dot line is I calculate using the power law temperature approximation. So for the case when the height is very small, the east cone size is very small, and also the X-ray luminosity has a not insignificant contribution, the temperature can just approximate as a very simple power law, like this. And then you can calculate everything analytically to get this time lag spectrum. So the calculation is very fast. You don't need to go through all this, the simulation, yeah, or integration. But here you can see there's some breakdown. So here the power law temperature approximation cannot capture really luminosity, but that's because in the low wavelength that you reach the region close to the black hole. So you need to consider the height of corona and the east cone size. And also here it will break down. That is because the calculation here is we assume the east cone size, the disk size is reached to infinity. So turnover is because the limit of the outer radius. But I think in this regime, in the UV optical, like the wavelength from the 1,000 to 100,000, this approximation works very well. So that means you can have the analytical function to fit with your data very quickly. So let's see another figure for the impact of the beta. So here you will see several size. So here I calculate the half-life radius and also the flux weighted size and also the flux variation weighted size. So for the reverberation mapping, the time lag is related to corresponding to this one. Okay, and another one is the characteristic size. But just for a reference, so you can see the size of the disk is in relation of all of these parameters. Okay, so of course, as we expect, if you increase the beta, that will increase your disk size. And here, if you familiar, so for the beta equal to 0, which is there's no wind, the temperature still follow the traditional physics model, then the number of the time lag you should use the number is 5.04. So, but for the flux weighted size, this is the number you use. But if you increase the beta, this number will change. So if you want to play with a different temperature slope, some number you need to take into account. And also, if you increase beta, you will increase the luminosity. So here I show the curve. The yellow one is I calculate the bolometric luminosity, and the green one is monochromatic luminosity. So it will also increase by the beta. So that means sometimes we need a very high high accretion disk accretion rate to describe the data, but you increase beta, you can have the same effect. Okay, another impact is for the color correction. So this can also increase the disk size. Okay, I can show you here. You can see the light curve will shift. Okay, I'll show you the power spectrum, the spectrum very quickly. And you can see that when you increase the color correction factor by a factor of 2, you can also increase the disk size almost by a factor of 2. But that doesn't really change your luminosity spectral shape. And here I also explored another two color correction factor model. This is motivated by the simulation and observation fit, but these two doesn't really change the relation. Okay, so here I want to highlight one thing. So we use a very simple thin disk plus lens pulse model, and I compare with another sophisticated simulation, which is the dot line here, and our simulation is the solid line. So I explored different parameters and also different spin, and obviously our simulation can really well describe their simulation. So now I need to show some case studies. So the case I use is for AGN, and the lag is from some other work. And also here I use one luminosity, like this luminosity measurement from this work, and I fit the time lag spectrum, and I use the power law temperature approximation, only 3 parameters. And the parameter space I list here. Okay, I'll just show you one case here. So this is a time lag measurement, and you can see I exclude this point because they are contaminated by the Brownian emission. And because still it's very hard to fit the data. So because the parameter they are all degenerate. So I use MCMC to try to study the relation between the degeneracy between these 3 parameters. So you can see that this is the accretion rate, and this is a color correction factor, and this is the beta. So for this case, because I use the luminosity as my prior, so I can kind of break the degeneracy between the accretion rate and the color correction. But you can still see the degeneracy between the beta and the accretion rate. Okay, that's all because based on the theory that would happen. And this is another case. You can see it's really hard to get the degeneracy between the beta and the m dot. But the m dot we can still get a constraint. It's a new case. Run out of my time. But here I want to show you the fit I got and the function of the black hole mass. So you can see that I couldn't really see the relationship between the black hole mass and the beta, which is the power index of the accretion rate. But I can see a slightly trend for the color correction and the black hole mass, and also the accretion rate of the black hole mass. But here I only have 4 cases, so that will be very useful for the future. The LSST provide a lot of light curves to really constrain or see the relationship between these two parameters. All right, so this is my conclusion. So first, we try to explore this kind of wind model, the power law rate, and this can indeed enhance the disk size and the luminosity. And I also want to say that the approximate power law temperature can apply to a UV optical, and we have all the analytical formulas. Okay, and then I think based on our work, we found that using the flux spectrum or SED can really break the degeneracy. That's why I think in the Josh's work of simulation, we try to all put the luminosity in his simulation when he generated a 3D set. Okay, so all of this work, even though it's a theory, but it's really important to double check with the most sophisticated simulation. And of course, in the future, we would like to explore more various model or some like a negative time lag from the Amy's talk. And all the detailed calculation will be published very soon. Thank you so much.
Thank you. We have time for questions.
So what about the mass rate of that you are losing from when you use your beta? Does it look anything like what people obtain when they model winds or they observe?
Oh, that's a very, very good question. I think the beta here is still the real number of the beta is still under debate. I don't think now people have consensus. The beta should be so like the parameter space I explore is from 0 to 1, which means that can make your temperature slope shallower. But I also found some other work, also from microlensing. They found that the slope can be steeper. So here I explored these 4 cases, these 4 AGN. It works well for the beta from 0 to 1. But I think for the larger sample, we need to explore wider parameter space. So I think in our simulation, for example, Josh's simulation and Henry's simulation, we don't limit it beta from 0 to 1. We really also explore the beta for minors. Yeah.
Maybe I missed it, but where is the dependence on the Eddington ratio? Because winds will obviously increase as
That's a good question. So maybe I should go back to. Okay. So this I plot the relation between the beta and the luminosity, but here I plot the Eddington ratio. So you can see that if you increase beta, that would also increase your Eddington ratio.
One more question. If there is no more questions,
Yeah.
I will make one comment.
Yeah.
I will not agree with your color correction, and you will see in my talk why I don't.
Great. Yeah.
Okay, so let's thank the speaker again. And the last speaker of the session is Jennifer Lee. And with this talk, we are returning to machine learning and complex mathematics. Oh.
Okay, is this good? Okay. Hi everyone. I'm so happy to be here. Finally putting faces to many familiar names on paper. Yeah, currently I'm a Schmidt AI and Science Fellow at the University of Michigan, and I think it's interesting program if you're interested in machine learning or deep learning. So if you or your students want to apply to this fellowship in the future, like just I'd be happy to talk. Yeah, but I'm moving to University of Illinois in the fall for a new position, hopefully with more LSST focus. Yeah, so today I'm gonna talk about my recent work as a field fellow, trying to apply machine learning and deep learning to uh, continuum reverberation mapping. So this work is just recently out on archive this week. I sent it out like right before my flight. Yeah, and so yeah. So thanks to all the talks before me, I don't think I need to go into too much detail about reverberation mapping again. But basically, RM is a method that helps us understand the inner structure of AGN by mapping or by monitoring the delay in variability signal from different wavelengths, let's say, from X-ray to your UV to broadline regions, and then to IR for the dusty torus. So for the purpose of this talk, I will be focused on the continuum art only, but the idea of the method or the framework is also applicable to other types of RM, or even say finding finding binary supermassive black holes. And hopefully by the end of this talk, you will understand why. Yeah, so I'm really excited about Rubin Observatory and also LSST. I believe it's the same for everyone in this room here. So I don't have to tell you like how good like this will be in the future. But I'm mostly focusing on the deep field because we will have very high monitoring cadence um, for many AGN in these 5 deep drilling fields. So even though the survey strategy hasn't been finalized yet, we're hoping to get daily sampling cadence of every other day or even daily. And this is great for continuum reverberation mapping because we have a rough idea of how big the accretion disk are. So they're like probably a few light days size. Yeah. So with all of these new AGN monitored in the LSST fields, it really opens up new questions for us to ask in AGN physics, right? I'm really interested in learning about the demographics of supermassive black holes, accretion disk, and then how these demographics or properties change as a function of redshift. And even just like going back to our like basic accretion disk model to learn uh, if they are correct or if we're missing something or what physics is the most important in driving an AGN. Yeah. So with the data from LSST, we are really starting to explore like RM or AGN science in a more statistical and systematic way. But there's just a small problem, right? We all know that there's going to be a lot of data, and we're super excited about it. But unfortunately, I have to say, currently there's just no good machinery for handling this kind of data, at least in RM. But I believe it's the same for many different fields as well. Like yesterday, we talked about having efficient Gaussian processes or other machine learning methods to do data. Yeah, so in reverberation mapping, traditionally there are like 2 like big categories of methods. The first one is CCF. So or sorry, the first one is like non-parametric methods, like such as CCF or ZDCF. So these are calculating some sort of cross correlation between light curves. So this is a fairly simple calculation, and in the era of LSST, this might be still feasible. But we also know that MCMC methods actually give us a little bit more information that ties back to our accretion disk model. Unfortunately, for these MCMC methods, usually it takes 1 to 2 hours for like a set of like light curves to converge. In the era of LSST, this will simply be no longer feasible. So, so I'm proposing to use this method called simulation-based inference to do reverberation mapping in Vera of LSST. So let's think about how do we usually study like physics, right? So we have some sort of theory we want to prove or disprove, and then we use observations as evidence to support our theory or see if there's something missing. But sometimes this is not simple, especially in the field of astronomy, because we have these complicated models where we have all kinds of complicated physics going into our model, and then we get these data from whatever we can get. Like for example, we can only get light curves, right? We cannot go to the accretion disk and measure how big it is. So we really try to find evidence from our observation to check if our theory is correct. And so simulation-based inference is just a group of methods that actually does this comparison between theory and observation using simulations. So based on your theory, so for example, your thin disk model, you generate a bunch of simulations and then you compare these simulations to your observation. So this in general is simulation-based inference. It doesn't have to be based in machine learning or deep learning, like your standard MCMC is the type of SBI as well. Yeah. So in the context of deep learning or machine learning, SBI just means that we're doing this comparison using a neural network because they are known to be very useful for understanding high dimensional data. Yeah. So for this toy project, we started with a very simple simulation setup. So we have a physics model that James kindly already talked a lot about. And then we have three different parameters where we're testing here. Sorry. Okay, yeah. So we have the black hole mass, accretion disk, and the inclination of the accretion disk. And this is a black body plus irradiated disk. Like I said, the setup is similar to James' talk. And then the transfer function is applied here in the 6 LSST bands UGRIZY. So with our accretion disk model, we do these forward calculations to simulate some light curves. And the intrinsic variability of these light curves are damp random walks. They are daily sample, and we sample for 180 days, so like one season of observe. Yeah, and then we put in a 1% Gaussian noise, and then we also perform a tenfold data augmentation. So that means with the same set of black hole parameters, we generate 10 different realizations of the stochastic light curve. So this is for the purpose of letting the machine learning method to kind of know what stochastic process is in this context. So yeah, so we have three input parameters, black hole mass, m dot, and cosine I. And then we have, from our simulation, we have this high dimensional light curve data as our output, which is a 180 by 7 array. So the first array is the time array, and the 6 arrays are the flux arrays. And then with this light curve, we put it through our machine learning neural network. So there are two steps here. The first step is embedding summary net. So this is basically the goal here is to try and reduce the dimensionality of our light curve data because we do not want to correlate straight with from 3 parameters to 1,020, 260 elements in our light curve data. Yeah, so we use a long short-term memory network. So this is a recurrent neural network. It is very useful for trying to find time-dependent features in your data. Yeah, so with this embedding summary net, we have summary statistics as our output, which is about like 16 features we find from our light curves. And with these features of the light curve, we use a neural density estimator to learn the correlation between our input black hole parameters and our summary statistics. Yeah. And then with this train method, we will construct a approximate posterior. So this is basically just a distribution of how black hole parameters and the light curve data actually correlate in the high dimensional space. And when we have an observation that we want to evaluate, we can put it into we can draw samples directly from the approximate posterior and find a posterior distribution of our black hole parameters. Yeah, so let's see how we are doing. Yeah, so for a first test case here, this is a very idealized case. There is no missing data. There is 1% possibility. Here are my prior ranges. And we train on 1 million light curve sets. So it's 1 million multi-wavelength light curve. And then test on 1,000 light curves that are independent from the training set. So here I'm plotting the truth versus the prediction of all three parameters. And you can see that we are constraining all three parameters quite well because they are all following a 1-to-1 ratio. So for the inclination, we can roughly constrain to about 5 degrees, and then for the black hole parameters within about 0.08x. Yeah. So the really good thing about SBI is that it directly produces uncertainty. So a lot of deep learning methods struggle with producing uncertainties. But because we are drawing directly from the approximate posterior, this is actually a probability distribution. So we have a uncertainty that directly comes from the sampling process. And so we compare the difference or the deviation between the truth and the prediction, and then compare that with the uncertainty directly from the posterior. We can find that for all three parameters, we can get a Gaussian of unity. So that means that we're actually getting a pretty good uncertainty estimation on the results here. Yeah, but there's no way that we're gonna get a daily sample like it, right? There's weather, there's filter gaps, and all that fun things that we always struggle with in reverberation mapping. And so, traditionally, people try to interpolate with different kinds of methods, for example, linearly or through like a damp random walk. Yeah, but here I'm trying to implement a different method. So SBI itself is very flexible. You can make the simulation however you want. So here I am just building the filter gaps into the my simulated data, and then train a new machine learning, train a new neural net. Yeah, so this is just the same micro data I described before, but with some U-band and D-band um, fluxes like just flagged out in the data. Yeah, and we can see the prediction and it's still pretty good. The inclination and all the parameters are a little bit less constrained than the idealized case, but still performs pretty well. I think the main difference here is that the inclination is a little bit less constrained, and this is reasonable because we're missing that highly cadence sampling of the data. Yeah. And then finally, we have been talking about how damp random walk might not be the real thing, right? So even though it's pretty good, we still there's still a very high possibility that Asian light curves are not exactly damp random walks. So in this case, I try to explore what happens when our simulation assumptions break down. So in this case, I trained the neural network on damp random walk light curves, but tested on non-damp random walk light curves. And so there are 3 different cases here. This is using light curves with power spectra of 1, and 2, and 3. And for a comparison, the random walk is a broken power. Sorry, yeah, broken power law with a slope of 2 and then 0 on the other end. And so we can see that in these 2 cases, the prediction is still pretty good. However, when the variability properties deviates more from the damp random walk, we started to see that these machine learning methods start to perform like a little bit weirdly. Yeah. So one interesting is when we're drawing these samples here, there's about like 10 to 15% of things failing. So this doesn't happen with the idealized case where the assumptions are correct. And so this tells us that if we have a lot of failed SBI evaluations, that means that probably we need to fix something in our simulation. So I think this itself is a pretty interesting insight into when we apply to real data. Yeah. One other thing I want to mention is that the accuracy actually correlates with the expected damp random walk damping timescale. So it's probably not very clear. So you can look at this panel. The color itself is the accuracy, and then this is, as you can see, there is a vertical gradient, but not really a horizontal one. So I'm thinking the neural network actually did pick up on something that is correlated with the damping timescale, but not with the magnitude of the variability. Yeah. So I want to go back to the beginning. We're trying to have this efficient method of doing efficient continuum reverberation mapping. And so the good thing about this method is that it produces something called an amortized posterior. That means once you train your machine learning method in the gray part here, you can draw the posterior for as many times as you want without additional computation time. So evaluating a light curve set would be less than 0.1 second per target. So you can go through like a single deep drilling field within minutes. The most computationally expensive part of SBI method is actually generating the simulations. Depending on how many parameters you have and how complicated your simulations are. For example, MHD simulation might not be the ideal case here because it's just too expensive. Yeah, and then the training time also depends on the how many parameters you have and how much training data you have. But for the case I've shown here is a few hours on a single GPU. So I think that's still pretty reasonable. The other thing I want to mention is that SBI is actually a very, very flexible method. So this is just a framework of uh, comparing our theory or model to our data. So once you have a setup for doing this SBI itself, you can always swap out the simulation using different sets of parameters in your accretion disk model or different physics, and then you can train the model the same way and then inference the model the same way to get comparison between different uh, say accretion disk model or AGN variability model. Okay, so this brings me to my conclusion. I think SBI is a very interesting way of like doing continuous information mapping. I'm planning to try to implement this method on realistic data or like more realistic setup and data in the future, but I haven't done that yet. So yeah.
Thank you. Time for question. No. Okay. I'm not sure what's faster.
Great talk, and I just wanted to say, like, I appreciate what you're doing by feeding in these non-damp random walk models to, because I do think that that's a concern that for a lot of these different techniques that we've been talking about, that the training data is exactly the same as what is as the testing data as well, right? And so you know, I mean, that's why I think everyone keeps asking, have you tried on observations yet? Because, I think that's a concern that if you tell, your model to expect a damp random walk, and then you ask how it does on damp random walk light curves. I mean, that's a problem always for testing these things on mock light curves. One thing I wanted to say in my talk is, yeah, as you point out, right, it's too expensive to make a million, not possible with these MHD simulations. But one thing that I want to encourage, and I'm happy to provide the light curves that are output from my simulation, just because they're not explicitly modeled in any way, you know, the reprocessed UV light curves. And so if you want to test these methods on mock light curves where you can put in a prescribed lag, right? So in the same way, it's still a mock light curve, but at least it has, you know, no assumptions about the model going in. So anyway, that I just want to say that's nice. And if people want access to the light curves I'm getting from my simulations to test their techniques on, I'm happy to provide those. So thanks.
Great. Yeah, I think that would be really useful. Yeah.
There was one. Paulina, right.
It's a little bit along the same ideas, because I was not sure how the mass and the accretion rate go into the light curves that you are then.
Yeah. So with a thin disk model itself, is these two parameters are fully degenerate, but because when generating the damper and the walk light curve, we follow the Maclaurin empirical relation um, the tau of the damper and the walk and the structure function variability. And so in this case, so we follow some empirical relations to go from the black hole parameters to the damper and the walk parameters, and then to the damper and the walk light curves. Does that make sense?
I have one short question.
Okay.
For sampling of the light curves, have you tried to use actually one of the proposed cadences for 1 year for deep drilling field?
So so for the
you mentioned gaps, but it's not just gaps; it's highly non-uniform distribution, right?
Yeah. So okay, so I didn't explain it in details, but in the new cadence strategy document, it says we're gonna try and do this filter swapping between U band and Z band. And so for this test case, it is just when the moon phase is certain under certain brightness, we put in the U band, and then the other we put in the Z band. I haven't tried the more realistic cadence yet, but one thing I want to mention is that once you have the simulated light curve, you can always downsample to the certain cadence you want and do this training. And,
yeah, I know, but it just makes a difference. That was my experience, unfortunately.
Okay. Yeah. So right now, there's less than half of the data itself.
Okay. So let's thank Jennifer again and all the speakers of the morning session. Time for coffee.
Paulina, no? It's Paulina. Yes. Yeah. Paulina. Paulina. Apologies. We should remount for the presentation. Sure. Spento. Si è spento il microfono. Is there a problem?
Huh?
Is there a problem with mic?
Is this? It needs battery.
Battery. So I will stand, Paulina Lira, I will stand 5 minutes. I will stand up 5 minutes or to give you with it's a with and 5 minutes before we have 5 minutes discussion.
Plus 5. It's not 20.
Okay, you're 15. Okay, so 15.
Yeah. So I'll tell you before 3 minutes. ¿Ahora sí o no?
Sí.
No. Aló.
No, es okay.
Esto está cerca de mi boca, ¿no? Sí. ¿Me duele las orejas? Es más así. Ok, más para adelante. Creo que es más así.
Adesso anche quando voglio perché qua si vede però per fare questo magari non si vede.
Ahí.
Queste che si vedono lì, però adesso esce diverso. Non abbiamo toccato niente. Adesso vedete manco toccare. Niente, provo allora a zoomare con la camera. Vuoi che provo un'altra volta a staccare il cara?
¿Y esto tampoco funciona?
Volevo... sorry, but don't see in the streaming. Sorry? We have a problem with the streaming. Not with the streaming. With the streaming. So we will wait for the...
They're trying to fix it. Esto no
We
funciona
will
tampoco.
start soon, just to resolve some streaming problems. We're counting.
Okay, she said zoom the image here.
Okay, so,
After
so what is the, so we will start. Okay. So dear members of LSST AG and Science Collaboration and guests, welcome to the second round of the reverberation mapping morning. And we are opening in the grandeur as in this morning with the Paulina Lira, related to the dust reverberation mapping with the VISTA telescope and the Vera Rubin Observatory. So the synergies, very important topic. Welcome.
thank you, everybody. So I thought to show something with lots of dust to motivate this talk. Okay, so we haven't talked about dust reverberation, and as we will see, it's very likely that we're going to be able to do some significant work using Vera Rubin. So, well, this is what we all know about reverberation. You just measure the lag between two light curves, one that it comes directly to us, and another one that comes a little bit later due to the reprocessing that goes on in some of the structures around the central black hole. In this case, this figure is about the BLR, but as we know, this can be done with any structure. In fact, this is a compilation by Caquette. He shows that you can do it with from the X-rays, for example, to the UV, to emission lines in the broadline region and the near infrared as well, although this is simulated, no actual data. And the lags are expected to get longer and longer as you explore structures that are farther away from the center. So while lots of people, this all started about the emission lines back in the late 80s and early 90s. Right now is all about exploring the accretion disk. But also we know there's been some significant efforts to try to apply this to also the dust around the AGN. So with Patricia, we did something in 2011, okay, with this beautiful object, and here we have from the X-rays all the way to the K-band, and you can see the strong correlation going all the way down to long wavelengths. But then the Japanese came and they blew us all out of the water because they had this amazing campaign with tons of objects. They obtained some beautiful, beautiful likers, fantastic correlation. And they were published the results in these three very, very important papers. But all of these were dedicated monitoring, looking at specific objects. And of course, people started to wonder, we need to do this with some more representative populations. We need to, these were all very nearby Cipher galaxies. You can see the names here, okay? So people thought, okay, we need to go to higher redshifts. We need to make a wider range in luminosities. Oh, sorry, I forgot this. So yeah, this came from the last paper of the Japanese collaboration. And they find this beautiful correlation, okay, which is expected. And the other thing that is important is that all the lags, okay, which you transform to the radius just by multiplying by the speed of light, are found further out than all the results of reverberation done for the BLR. So this is very nice result that points to the stratification of the structures around the central massive black hole. And what is the correlation, that theoretical correlation that you expect to have for the lack of the dust? Well, it's just that everybody talks about this torus, and for quite a while, when I was just starting to work on this, I was thinking, why a torus? It sounds odd. Why would this material just fall in form a torus? And actually, it's more like it's a carved pumpkin. Okay, it's not like the torus doesn't want to go inside. It's just that it gets destroyed if it goes to a radius, which is called the sublimation radius, and is given here in this expression. Okay, so it's like this pumpkin where the dust only populates from the sublimation radius outwards. Okay, and another paper by the Japanese collaboration showed how this has a potential as a cosmological probe. Okay, because whenever you have a distance that you can infer from other properties of your object, then you have something that can be used as cosmological probe. And in this work, he compared the distances derived with Cepheid stars in nearby galaxies, where with the measurements of the distance. We're going to be swallowed by a black hole. Okay, I think. Okay. Okay, so he compared the Cepheids in nearby galaxies with the radius inferred using the reverberation of the dust sublimation radius. Okay. So, as I said, all of this was done with very dedicated pointed observations of well-known galaxies. And people wanted to extend these to objects at higher redshifts and also a wider range in luminosities. And there were these two works, one by Liu in 2019, one by Yang in 2020. And both of them, what they did was to use wise light curves, which are the points here in blue and red, and in this case in red down here. So they compare optical light curves, okay, that they compiled with the wise observations. As you see, the wise data, because you also show the figures with your best examples in this kind of papers, of course. So the wise data you see is very sparse. Okay, is the time base is not very long, and also the monitoring is quite sparse. Still, they managed, for example, here clearly the errors, the scatter is significant, but they still managed to pretty much follow the sublimation line that had been found by previous works. In this case, the work was done with PG quasar, so it's not so much about extending in redshift, but extending the relationship in luminosity. So then, long time ago, Paula was still a student. Paula Sanchez was still a student. We were working on variability, and then the Ultra VISTA survey was their aim was just to get this super deep image of the cosmos field. And we just kind of said, hey, hello, do you have time resolved data that we can say, yeah, sure, no problem. So they gave us the single images for each time that they looked at the cosmos. field. And Paula did all the reduction. I mean, not the reduction, the images were reduced, but she did all the photometry, all the calibration. And we obtain light curves like this. Now, this is done with the VISTA telescope, which is a near infrared telescope. So our wavelength coverage goes approximately from 10, from about 1 micron to 2.2 micron. But still, and again, this is shown in the paper, but it's one of our most beautiful curves. Okay. And you can see that the sampling of the light curves is not very good because UltraVista was not designed as a survey to look for variability. But still, it's good enough for us to do some work and some preliminary work about the difference in variability between type 1 and type 2 sources in the Cosmos field was published by Paula in quite a few years ago now. And we decided to do try to do reverberation. Now, what are the considerations you need to have here? First of all, not only theoretically, but clearly observationally, there is a dip at about 1 micron, which is where the disk, the emission from the accretion disk is coming down, and the emission, sorry, this is the other way around because this is the weight of this frequency. So this is the disk coming down, and this is the dusty tubes going up. Okay? So you expect to have this crossover between these two components at about 1 micron. Yeah. So this shows the rest frame SCPs of our sources. Okay. First of all, we took all the AGN in the Cosmos field, but we only kept those that show variability in all bands, and we restricted our redshift range between 0.3 and 0.8. Why? Because we wanted to map this crossover, okay, using either the Y or the J filter curve to the left and the short K to the right. And for the nearby objects, okay, this is where the K filter is found. For the higher redshift objects, this is where the K filter is. And here you can see the Y and the J depending on the redshift. So we are mapping the disk on this side and the torus on this side. And you look at this like these photometric points, which is just total flux. And they look as if maybe there is a torus here, maybe not. Well, it's so much better to look at the RMS data, okay, the variance in the photometry. And clearly here you do see, okay, the V shape, okay, because this is not all the light, this is the light that is varying, okay? And clearly you see that signature from both sources are clearly there. So we did it very, very carefully because we know that you can measure things that are not real doing all of this. In fact, we stay clear of anything that assumed something about the variability. We stay clear of traveling or anything of that. We just wanted to go old-fashioned, and we use just interpolated cross correlations. Okay. And I picked just 4 sources here from the paper. The cross correlation are these green points. Okay. Then you do the usual. Okay, so these are 3 good results. That's the bad one. Okay. Okay. Then something else. We got the lags or lux or luminosity range was not very big. So our results just looked like a scatter plot right there. But something was odd. Most of our objects were below where they were expected to kind of align, okay? And this is estimating the visual luminosity from the B band or from the X X-ray band, and there's an odd object here, but whatever. All of our lags like below what we were expecting, and we didn't know why. We spent just months and months and months just trying to do anything that we could think of until we realized that Minesaki had told they had done it all along, that it is necessary to do it. It's just as basic as that. But if I looked at the other works that that I put here, okay, they don't do any K correction at all. So I was thinking, why do we need a K correction? And they don't. Okay, so it has to do where exactly where our surveys are sampling the rest frame emission from the dust. So for these people, things are pretty flat. But we are this orange here, okay, where the changes are very abrupt. So after we follow the same recipe as Minesaki, okay. Oh, sorry, it seems I don't have the slide with the K corrections. I don't have. Oh no, these are the K corrections. Sorry. So then we are still kind of scattered out of thoughts, but we are in the right place. So it's very, very important to know that the torus, of course, needs a strong K correction. Okay. What I want to emphasize here is that we were able to find lag even at the very edge of our redshift range. Okay, so these are objects that really are hardly just probed by the K band. Okay, so we can do it. It's important to learn about the K correction, but what does it have to do with LSST? Well, Sebastian Honing 10 years ago said, let's do it. Let's do it with LSST, and this can be used as a cosmological probe. And he gave us this modeling, okay, and he went all the way to redshift 1. Okay, so I looked at it myself. Okay, I took those objects that we just managed to show that it can be done, and I took them to lower redshifts. So the purple point is if they are completely local, 0 redshift, and the yellow points if they are a 0.1 redshift. Okay, and yes, the Y band for the very local objects will start to probe the dust emission. I'm not so sure that you can do it going all the way to redshift of 0.1. But the thing is, you're going to have lots of filters in order to follow the variability of the disk very well, which is something you need to subtract from the light curve, from the dust. And having very nice monitoring of what's going on here maybe means that even for objects at redshift of 1, the correction for the disk variability will be feasible. So that's just to finish. And here I just give some questions that we would like to answer once observation can be done with LSST. Thank you.
Amazing. Thank you so much. Thank you so much. It was a wonderful talk. So please have time for questions. Specifically encouraging the early career scientists, newly coming guests, members of the AG. Please.
Thanks for the talk. I was curious how the clumpiness or smoothness of the dust can affect these results, what we expect from them.
Yeah, that's exactly the kind of thing that you want to learn once and for all, because this, and this is one of the concepts here. Are torus emission models telling us the truth? Because there are the continuous models that also there are results that say that the good function of the emission might be coming from some polar dust located in a polar configuration. And that has been, I think, even using gravity has been confirmed that there is a good fraction. So yeah, my quick numbers last night interpreting tell me that we're going to have hundreds of thousands of objects. And I think we can finally start to explore parametric space, okay? And those structures by no way are going to be the same from one object to the next. And we're going to be able to do much, much more than what has been done up until now, including things like that. Yeah, find out about, yeah.
Thank you. Any other question, comment? Yes.
I'm not in this field, but the question might be very naive. But I'm curious how the model-dependent dust SCD, especially from towers, actually change the K correction.
You mean the models?
I mean, you show the dust the
Yeah.
SCD
Oh,
from
yeah,
the
yeah,
dust
yeah, yeah.
towers, right?
Yeah,
It's
yeah.
a one model, right?
Yeah, okay. So I just overplotted them here. Okay, these are just models, but the correction proposed, and that's again a very interesting question because the correction Minnesaki proposed was done completely in a completely empirical way. It was not based on models, and in fact the models do not predict this K correction. They predict something quite different. So again, things that has to be studied and understood and discussed, because right now this was driven by data, not by models.
Thank you so much. If no more questions, we can also during the discussion. And now we are proceeding to, let's welcome and thank Paulina, and we are welcoming Professor Bozena Czerny, and have her talk related to the broadline region, reverberation, mapping, and more complexities. So we will encounter here more complexities.
This is next slide. Okay. Okay. So I will talk about broadland region reverberation mapping. I have several collaborators, as you can see, because the topic is quite complicated. Oh, it's not working. The middle one. Oh, sorry. Okay, so why to do broadland region reverberation mapping? There are three main good reasons. First, broadland region is quite complex. We already saw that on a few plots, few pictures. Then broadline region serves as a primary tool to determine the black hole mass in an AGN. And then if you need statistical studies of galaxy evolution, you must know the black holes there. And finally, broadline region also can be used as a distance indicator, which Paulina already mentioned during the previous talk. And of course, Vera Rubin Observatory will give us many more objects, because now, by now, the reverberation mapped sources are of order of 200. That plot you already saw several times. It was stolen from Erin Kara. Only I did one change because I wasn't sure why she's sorry. So this is going back, and this is going, and this is laser. I wasn't sure why she and many people finish the disk and then start broadline region, while I think broadline region actually is related to the disk in the form of the wind, something like that. Anyway, there are two basic approaches to reverberation mapping of the broadline region. Historically, first is a dense multi-wavelength spectroscopic monitoring of selected objects, and that gives a very detailed information about each source. But then there are options for massive monitorings, particularly important for the other two arguments, like massive black hole mass measurements and cosmological applications. So as I said, broadline region was mapped already many years ago, probably before some of the people here were born. Here you have an example of the argument that the broadline region is spatially extended. This is the study done for NDC 5548 by Ari Vandel and collaborators in 1999, where they measured the delays in different emission lines in the range from 2 to 30 days, and all those delays nicely correlate with the full width half maximum. So that also served as a proof that the broadline region is approximately in the Keplerian motion. Jumping to most recent results for the same source, NGC 5548. Now with the current data, you see that even emission in a single specific emission lines is spatially extended. Here I enlarge the region for carbon 4, where the measured delay covers the range from 0 to 40 days, right? And it shows actually quite interesting two-peak structure. I liked this two-peak structure quite a lot because this is a digression. I'm developing a broadline region model as a dusty-driven wind, and from this model we can calculate the structure of this clumpy wind, and from this structure, for the parameters of NDC 5548, we calculated how this reprocessing function should look like for inclination of 40 degrees, and it does show two peak structure. Anyway, I should mention that broadline region is partially resolved by gravity. On the other hand, it's only for few sources. And then here is the original plot for the first source, VC273. The precision of this mapping is not very, very good, because it's very impressive interferometric data, but nevertheless it only shows more or less the consistencies with the view that the broadline region is flattened, but it does not allow to tell whether it's a stream or a fairwind or conical outflow or anything like that. For that, we do have to make the reverberation map. And then if we do not concentrate on a single source, but on many sources, then the key concept, which was already mentioned by Paulina, is this radius luminosity relation, when you relate the radius versus the monochromatic flux, traditionally at 5,100 angstroms. And here you see again one of the oldest plots of this type from Vandel et al. 1999. You see the more or less slope consistent with zero 0.5 with the square root of the luminosity. And later, more objects allowed to determine this radius luminosity relation much better. This is the most successful plot shown by Benz et al. With the smallest dispersion, then you have the radius luminosity relation well fitted, and this opens the methods to determine black hole mass, because either you measure the time delay and the velocity from full width half maximum or sigma, whatever, you can calculate the black hole mass. And then if you have just a single spectrum and you don't have the time delay, you measure the luminosity. From that, you measure the expected time delay, and again, from the line width, you measure the black hole mass. But if you measure the time delay separately, that opens also a way to apply the idea to cosmology, because then if you measure the time delay, then you have on the right hand side the absolute luminosity of the source. So from the time delay, you calculate the absolute luminosity of the source. If you have the absolute luminosity of the source, and you know the coefficients, of course, up there, then you can calculate you have to combine that with the observed flux. You calculate the luminosity distance to cosmology. People in that paper were not yet brave enough to do that, but we are trying. We are trying. The problem is that with more measurements, for example, in H beta region, we are doing actually much worse than in the original plot by Benz, because when we included measurements of high Eddington ratio sources from Jimmy Wong and his collaborators and several other measurements, then you see the dispersion rapidly increased. But we are also constructing radius luminosity relation using all the data which we can gather from everybody, including Paulina and maybe few more in the audience. We even have the radius luminosity relation for Fe2 in optical and UV, but we don't use that for cosmology. We wanted to use H beta, carbon 4, and magnesium 2, but finally H beta coming from so different sources in the sense of both Eddington ratio and working groups, that was not really usable for cosmology. But when we combined 150 time delays altogether, taking magnesium 2 and carbon 4 delays and scaling coefficients, we got some cosmological constraints on omega matter, but this is not really something which is really impressive. The number of sources is not large enough. The sample is not is too small to divide it into subsamples. Otherwise, the dispersion is large, and delays taken from different groups, different methodologies. This is really a catastrophe, honestly. And we expect that with LSST, this will help if one group of people will calculate those line delays in a systematic way. Of course, we will have a lot of AGNs from LSST, and if you look at the number of supernovae and the number of AGNs, it's kind of comparable. Only what you can notice is that supernovae will always cover the redshift range only to 1.2 for the reasons I cannot answer, but that's what they say. While of course quasars can cover redshifts up to 3.5, let's say, quite comfortably. So we did simulations to check how reliable, whether we can determine the line emission reliability, taking into account that LSST, of course, is the photometric survey, not spectroscopic survey. And we notice that if we take the main survey, realistic, I mean, cadences from the system, proposed cadences, it was not very sensitive for cadences. Then for bright sources with luminosity, monochromatic flux at 3000 above 45.7, something like that, we have a very good agreement between the adopted time delay and recovered time delay above the redshift 1, more or less, because then the time delay is of order of 400 up to 1000 days. So whatever you do, it does not matter as long as you have a decent photometer. That's important. In the case of the faint sources, you do not sample well the time delays you really need. I expected Swayam Panda to say more about that, but he will not give a talk, so I can only tell you that in the simulations, we simulated the spectra, the contamination by line, whatever, but we didn't use any machine learning, anything like that. It's a simple chi-square method for time delay, like that, to recover. And actually, I was supposed to talk only about the broadline region, but I couldn't avoid temptation of saying something about continuum time delay, because, and in particular, in application to cosmology, there was a lot of talk about the continuum time delay, but also it was mentioned that you have the problems, whatever. So the idea to use continuum time delay for cosmology is very simple. It comes from the paper of Collier, 1999. Looks kind of basic, like you measure the time delay and taking into account that you know the properties of the accretion disk, you calculate the luminosity distance from a simple formula, and you are there. The problem is that when Ed Cackett used that method in 2007 for a sample of, I don't remember, 10 sources, something like that, he got on average the Hubble constant 44 kilometers per second per megaparsec. And for NGC 5548, he got 15 kilometers per second per megaparsec. This is another way to say that the time delay did not was not consistent with Sakura-Sunyaev disk. I think during the few recent years, we understood really what is happening, and the paper of Hagai-Netzer was really excellent, stressing that what you see is mostly actually the contamination by the continuum from the broadline region. So we modeled that in the published paper as a scattering, but then you cannot really disentangle two sources of time delay. So your photons come towards you directly from the disk, but only a fraction, and then a fraction is reprocessed by the broadline region. And on this right-hand side plot, which we got only a few weeks ago, we were able to measure the time delay, I mean, to model the measured time delay for NGC 5548. The data are black points. The model, our model is brownish points, total model, and this time delay really consists of the delay from the disk. This is this lower part, and from the broadline region. And here the key point to divide those two time delays is the Balmer edge. So in this plot, we still do not show the errors because we didn't see. It's just an experiment. We have to write the software for data fitting. But when we now use only the disk delay for cosmology, not the total measured delay, but the disk delay for cosmology. Now we are getting 69 kilometers per second per megaparsec. I cannot tell you what is plus minus for in that case, but at least it's a considerable improvement from this 15 kilometers which were obtained by Kaket. What of course shows this, and I do not have time to elaborate more, is that if you want to separately reproduce the disk delay and the broadline region contamination, you have to fit at the same time the SED, at least mean SED for a spectrum. And this is what we are doing. I mean, not fitting, but at least checking whether the Balmer edge is consistently seen in the spectrum as well. So continuum time delays also can be used for cosmology, but then you have two problems. First, you really need to know not only the redshift of the source, but also a single spectrum. So it's not enough to make sure that measured object is an AGN. You need a spectrum. Then, of course, for continuum time delay, only deep drilling field is dense enough. And then when we took, or actually Francisco Pozon Núñez took the cadence which was proposed for deep drilling field, exemplary cadence, then he could not measure the continuum time delay for lower mass objects, only for high mass objects. So then we made an experiment that 10% of points we assigned according to these accordion points discussed by Neil Brown. The rest 90% are from the older cadence. And then we averaged over seasons, not 10 years, but 10 years cut into seasons, start up. In that case, it looks like errors are smaller, but we see the offset from the proper solution. I think during the first day, somebody else mentioned this kind of offset. And we also do not understand what is the source of offset. And of course, if you measure several thousand of those sources, and then you claim cosmology parameters, the offset is absolutely critical and dramatic. So this is overall my summary. We will have a lot of detections, I think, from the main survey for the emission lines. But really the accuracy and systematic errors are the problems. If we want to claim something about the cosmology, then for deep drilling fields, it's also a problem of systematics eventually. Thank you.
Thank you so much, Bozena, for raising really important questions, comments. So now, please, we're opening discussion part. Here we have the accordion cadence mentioned, which is proposed by LSST community.
Yeah, thank you, Bozena. I was interested when you said you needed to have a spectrum to be able to disentangle the continuum from the lines.
Yeah.
But what happens if the quasars vary, and so if the emission line strengths change between the spectrum you measure and the start of your...
Well, unless you are unlucky and you have a changing look AGN, the variability is not strong enough. So I think mostly this continuum goes up and down a bit, but it's also not dramatic. Even in 10 years, it shouldn't be dramatic. So, but at least one spectrum we must have, at least one spectrum. Otherwise, there is this ambiguity. between different parameters. You have the height of the corona. Usually people compensate everything with the height of the corona, but then you cannot match the SED. This is what we checked. And
Thanks for the talk. So I'm curious about the Hubble constant measurement. So would it be limited to the type 1 or type 2 AGN, or it doesn't really matter?
here, oh, it is absolutely type 1 only. We don't even cross our mind to think about type 2 because we need really good type 1 spectrum with emission lines and with Balmer edge, Paschen edge I didn't mention. So then we can control all the parameters which are involved. Optimistically speaking, for Sievert's tools, forget the idea.
Another question?
Bozena, I was curious. So in order to derive the disk, you had to take out all the line emission and the diffuse emission, all of that you did?
No, we were trying to reconstruct the mean spectrum at the same time, which included the disk emission, line emission, and Balmer edge. So you have to fit both things at the same time. We didn't fit exactly. The student was still doing that by hand because it was a pilot study. But now we have to write a software for automatic fitting. But yes, because your spectrum, for example, if you play with the height of the corona too much, your spectrum starts to bend in UV or start to go up in UV, you know.
You say that 20% of the light comes from the BLR.
Yeah, this is what he assumed in this model.
Okay. And so 80% comes from the disk?
Yes, directly.
Okay.
Yeah, but still the effect in time delay is quite strong because as Hagai Netter showed in his paper, approximately you calculate the time delay as time delay from the disk times flux from the disk plus time delay from the broadline region times flux from the broadline region. But the delay from the broadline region is 10 or 10 times longer. So if you have factor 20%, then it means that it contributes factor 2 into time delay. It's not quite true, this formula, but approximately it gives you the idea. So it is important, as you can see.
Thank you. Thank you, Bozena, once again.
Okay.
Thank you so much for this wonderful talk. And now we have 10 minutes discussion. So we have a morning reverberation, 2-round sessions, and there are some complexities reason by the presenters. Also today we have the Rubin Science workshop discussion related to the accordion, to the optimization cadences, and the metrics will be not finished before the start of the LSST. It will continue further. So any comments related to this or anything else? We had also presenters, early career scientists, and as a community, we appreciate if you interact, for example, as well-established senior scientists with the presenters. This morning we had Jennifer Lee, we had Amy Secunda, we have some other people. We have also James Piano here. So, yes.
So it's a question. For the reverberation mapping study with a lot of samples, especially for broad line, do people want to exclude either changing multi-state AGN, the drastic change between type 1 and type 2? Is that including that sample is bad, or usually doesn't matter much?
Great question.
Would be, for me, it would be bad because it would spoil my cosmology.
Thank you.
Sure. I mean, that there are outliers by definition, but they are very interesting to understand too, so that we learn about how these sources work when they are not in kind of steady state. So uh, I'm sure those that don't want them, like Bozena will call somebody and say, "Hey, look at these objects," and that person will be very happy because there's lots of people working on them. Good for everybody. I have a question about the hydrodynamical simulations by Amy. Yeah. Because I remember a few conferences away, people showing simulations, kind of showing 2D things, and they were crazy, and they couldn't even understand what was going on, Proga, that kind of people, okay? And they were starting like from the beginning, like you have the black hole that suddenly starts to repeat. And I remember for them was even hard to see when the disk was gonna achieve some kind of steady state or something like that. So I wonder whether your approach is different, that you assume that the disk is already there and then you put it to work.
So yeah, so I actually think those kind of simulations have come a long way. And also, I think you kind of have two main categories of hydrodynamic disk simulation. You have the protoplanetary disk simulations, where the picture is still very unclear because you have to deal with the fact that it's weakly ionized and all these non-ideal MHD effects, which are very troublesome. And then you have the AGN disk problem, which is actually simpler because we are more strongly magnetized. So I think in the MHD simulation community for AGN disks, there are people who are doing these big simulations where they accrete a disk and they pretty robustly form a disk that is often supported by radiation pressure or magnetic fields, depending on the different simulations. Um, and so I do think that those are becoming a lot more robust. What I'm doing specifically is because I'm trying to study this reprocessing, which requires, doing a really careful radiative transfer calculation for at least two different groups of radiation. Uh, I'm actually just doing a local approach. So I'm not accreting a disk. I initialize my simulation in radiation hydrostatic equilibrium. So I assume, an initial mid-plane temperature and density and, optical depth and calculate what the stable vertical structure would be. Then I start the simulation and I wait for it to settle into a steady state. And then once it gets there, then I actually start studying these light curves. So yeah, uh, so my simulations are in a very steady state, and so yeah, but even in these bigger, more dramatic simulations, it takes time to get to this steady state, but they do seem to be in a steady state. But these disks are turbulent, so they're constantly changing and evolving with time, uh, but more cyclically, if that makes sense.
Maybe some other comments? Yes.
Just on this topic, I tried to talk to few people doing global simulations, and I wanted them to show the power spectrum from their simulations, and they usually refused.
Great.
So thinking back to yesterday and going back to the observational side, one of the points that came up repeatedly yesterday was the idea that we would benefit from having merged light curves with precursor surveys, right? And have the time domain information from CTF and so on before we start with LSST. Is that also helpful for the reverberation mapping, or do we need to start from scratch with the 6-band colors from LSST? Just a general question.
To add.
Oh, to add.
Start as baseline and then expand rather than starting from zero.
Yeah, I mean, I don't know for the discontinuum reverberation that might not be necessary. Yeah, I can pass it, but for these long negative flags, yeah, anything to extend the baseline is useful. But you also introduce and have multiple, seasonal patterns, multiple, similar but still different, multiple cadences. You do introduce more timescales into your data, which, you're looking for one specific timescale, but now you have all these other timescales. I do think it will confuse methods.
And then for like this part, I think there's been some observational evidence that in different year of monitoring for the very intensive disk RM from multiple groups that it seems like the disk properties change from like year to year, and so in that case, then adding in the ZTF observations might not be directly relevant with LSST monitoring. Oh yeah, that would be interesting as well. Yeah.
So it means that all this science we are speaking about can start to be done only in the 2 years after LSST has made observation, has made a cutoff with this data. Cannot be starting next fall.
Yeah, for the network like I'm building, I'm like trying to aim for the first season. After it's done, then I just implement the light curves into that. But this can also the same method can be trained for ZTF data as a practice or example. Yeah.
I think having the longest possible light curves is the way to go for several reasons. You want to study you want to extend the power spectrum all the way to the lowest frequencies possible to see whether there's another break or something like that, compare with X-ray binaries, etc. Then also any changes in the object, things that we want to understand, how they are triggered, what are the behaviors, which parts of the structures are really changing. And then, yeah, how often do they become weird? I mean, are changing state of just a tail of some systematic changes that are happening all the time? How do they correlate with black hole mass, with accretion rate? I mean, there's just so many things that we want to understand, and I think having the longest light curves is just the way to go.
Okay, this is probably not related with the discussion you're having, but maybe a message from what we learned using the ultravista data is that gaps are really important. And please take this into account when doing your time lags. Also, it would be nice that you take the to test like what we did with ultravista, like the effect of sampling gaps. I don't know, different things. These plots you were showing that you didn't have the time to explain. Because we have seen results from WISE in particular, where at the end the timing acts are just gaps. And I think people are not aware of this. Like Javelin is also very good at finding lags in the gaps, and methods like I tend to be better. They are, of course, very old-fashioned. Maybe people don't like them, but I think it's super important to compare because we learn in the bad way. I was working on this for the last 5 years, and then you find the solution. And yeah, it's tricky. So take your time and don't believe the first lecture you get from Javelin.
I could add, if you have very, very, very good data, Javelin will give you the right answer. But if your data has some flaws, then think twice.
Thank you very much, Paulina and Paula, for this question. I mean, this is about, let's say, irregular cadences, gaps, sampling. This is something that all of us working on acquiring data and real observations, and many of us here have been doing this for the past 20 years, if I may say. A lot. Yeah. But I mean, and I absolutely agree with the comment that Paula just made that uh, testing more than just one tool is absolutely necessary in providing comparisons of the results. And that's something that the project that we are always trying to do. And I just want to also comment that there are really many tools already available now. And Andjelka mentioned one tool this morning about this discrete correlation function, the ZDCF, which was developed by the group from Professor Tal Alexander a long time ago. And it was written in Fortran, and that was quite a challenge to use. So what we did, we a few years ago with our PhD student, we developed. We wanted to do the Python wrapper, but that was not working. But so we upgraded a little bit the tool, and we translated it completely into Python. And that notebook is actually available on Astro Data Lab. So, and Astro Data Lab is one portal where there are many practical examples, but also others as well. And I really encourage people to try not just this, but any other methods as well. And I know Viktor Okniansky also developed one tool for, let's say, an upgraded ICCF, also in Python. So really many different tools. So thank you
so much.
I just like to comment on the different type of tools. Like when I was a grad student, I did a work on comparing ICCF, CDCF, and Javelin, and the simulations are model for like SDSS arm, and it's for a Pauline region. So, but like I think it's similar. Like we have like gaps in there, and we kind of like show how each of the methods have like their own advantage and disadvantage, and it's like all written up in a paper. So yeah.
Thank you so much. And massive thanks to the community for great interaction and young scientists. And now we have a special guest, Megan Davis, coming through the matrix glitches, and we will have privilege to hear a new member of the AGN community, a career scientist, and she will talk about the determination of the binary, supermassive binary black holes, something in continuation on Maria talk, and we're preparing, and we are really excited to hear her important work.
Thank you.
Megan, you're more than welcome.
Thank you. Can y'all hear me? Okay.
Yeah.
Awesome. So hi, I'm Meg Davis. I'm a bit late on giving this talk. I'm a bit late today. But thank you all for allowing me to still sit and work with you. I am a PhD candidate, 5th year, working with Jonathan Trump, no relation, his joke, not mine, at the University of Connecticut, along with some other fantastic collaborators, Jesse, Neil, Maria, Hittenwood. Yeah, today I'm going to chat with you all about identifying reliably, there's an asterisk there, binary supermassive black holes with Rubin. So first, it's really important to me to get to know the humans behind the science. And so now you get to learn about this human behind the science. So yeah, I'm a PhD candidate at the University of Connecticut. I'm also a grad research fellow through the NSF there as well. I did my bachelor's at Michigan State university, I did all sorts of research from astrophysical, neutrinos, exoplanets, all the way to galactic chemical evolution, jack of all trades, master of none. Also, for anyone who works in SDSS 5 and black hole mappers, reverberation mappers, I think you're certified. I'm also the keeper of the parent catalog, and I did all the cross matching between SDSS and all the other major surveys. So, hi, nice to meet you. I'm the I'm the one behind your data, and this is a note for me to also give a very special thanks to all the survey scientists, software developers, everyone who's working really hard to make these surveys happen. Y'all deserve so much more credit than you get. It's hard work, so you're very much so appreciated. So let's talk about science. I'm gonna try and speed run some background, the barest of minimums. Again, I'm out of place. So there were other folks who were going to give you more context before me, or yeah, especially on Monday. So I might miss some details. Just ask me or talk to me later, okay? Oh, no, that's right. Cool. So how do we get binary supermassive black holes? We typically form them, we think we form them through galaxies. On the right over here, I have a bunch of SDSS images of emerging galaxies. We typically call these dual AGN. They're not yet gravitationally bound to each other. And that's a really important distinction, not gravitationally bound yet, large nuclear separation. You can pretty much tell the difference. You can very much tell where the AGN are in these. Over on the right, this is one of like my favorite images from the Duffel et al. Paper in 2020. Simulated simulations of what these systems could actually look like when you actually get down to parsec and subparsec scales. When these supermassive black holes have finally sunk into their gravitational potential wells, they're finally gravitationally bound to each other. You get a circum binary disk, you get streams, you get mini disks. I think this is neat. In my work, unfortunately, I'm ignoring the streams and the mini disks for now, and I'm focusing on the circum binary disk. It's a future consideration. Preempting the questions. Finding these objects will, of course, further our understanding of gravitational wave physics. It's extremely important, especially with the big nanograv and IPP images that came out last time. These objects are likely the source of the gravitational wave background, though the string theorists may argue with one. With studying these objects also helps our understanding of galaxy mergers, merge rates, and galaxy evolution in general. The issue is that optically, photometrically, we have hundreds of candidates, no full confirmation detection. We actually have hundreds of candidates across the electromagnetic spectrum. And outside of the optical regime, some of those candidates are really, really promising. That's not my work though, so I won't really comment on it too much. But there's a lot of exciting work being done by some fantastic scientists. So what is the issue optically? The issue is that we're searching for periodic signals. Those periodic signals come from a variety of sources, but mainly my work, we're focusing on Doppler boost, relativistic Doppler boost. We're examining these black holes, the primary and the secondary. The primaries, the bigger one. The secondary, the smaller one, is moving pretty quickly, relatively quickly. And so, yeah, we see modulation of the light curves. There are a lot of assumptions, underlying assumptions for this model. The orbits are circularized, mass ratio arguments as well. Most of what we're looking for is a smooth periodic signal. So there's an asterisk up here because there are 1,000,001 ways to make periodic signals with APN. If you like QPOs, also periodic accretion, hotspots in the accretion disk, many ways. But this is one of the primary ways we're looking. Doppler boost is also really nicely connected back to gravitational wave physics. I think Maria talked a little bit about that maybe. Yeah, so we're searching for periodic signals. And when humans are searching for a particular pattern, we're pretty good at finding it. Wrong. So we can't really confirm optical photometric detection of binaries because we're confusing it with quasar variability. So this is a case study of PG1302. The kernel A is the from Graham et al. 2015. It's a beautiful light curve. Look at that sine wave. It's pretty nice. Unfortunately, Van et al. 2016 a year later and said, hold on a second, that's not what we can actually model that with quasar visibility, accretion disk instability. So we need to be cautious. And in fact, we suspect that a lot of our candidate samples are contaminated with false positives because of this. Quasar variability causes two main issues. As like your Eddington ratio goes up, your structure function down. So the light curve, depending on what method you're doing at it, you might get a pretty good fit. You might get a pretty I-squared out of that. False positive. If you have suppressed Eddington ratios, noisier light curve, you actually just completely obscure the periodic. You can't disentangle the two. So it's a complex problem. And many smarter than I are also working on this. So hundreds, thousands of examples of finding binary sustained periodic behavior where there are none. Like I said, we're really good at fitting waves to data where maybe we shouldn't be. So is there hope? Of course there's hope. That's why we're all here. It's Rubin. Rubin's hope. ZTF is a source of hope. And a few things for emphasis here, but Rubin's cadence, baseline, and expected number density may help us solve our problem. We suspect that quasars may signpost as like looking for quasars, make fine binaries, expect there to be very bright emission. But we're still sifting through the AGN, all the AGNs. I might use those interchangeably, sorry. So there are a few points. I know y'all know this, I would hope. But Rubin will produce like 20 terabytes of data every night. That's a lot of data, a lot of things to sift through. We're looking for needles where the haystack, right? And yeah, millions of active collective nuclei, which is pretty fantastic. If I have enough time at the end, I'll show you the outreach fact about the Rubin images and connecting to Las Vegas. Yeah. So how exactly can Rubin help us? We don't quite have data yet, so we need to fake some data. And can we triage that data? We're going to have 20 terabytes every night. That's a lot of data. And are there any types of quasars that are going to give us problems as we try to solve binary detection problem? And to do that, yeah, so I had to first make some data. And as with all things in life, you fake it till you make it. So you fake data until Rubin makes it online. So I first started with a variability model. I started with the damped random walk. And I need you all to know, I mentioned this a few times, the code's really flexible. We all have favorite models for variability. And a lot of people might prefer something other than the DRW. And that's all right. The code's pretty flexible. I can put in any model that y'all desire, but I had to start somewhere. This was easy and simple. So I did it. So I started with the damped random walk. I have a broad range, a broad uniform range of quasar properties like mass and Eddington ratio. So I was able to create these base. From there, if I wanted it to be a binary, I would add some periodicity model. So the smooth signs from Doppler boosting, like I talked about earlier, but then we got actually more creative too, and introduced some sawtoothy type waves to mimic like periodic accretion, because we just wanted to see, could we pull those back out after injecting them? Cool. We combine those, and then we make real, very idealistic simulated light curves. Or in this example, with a deep cadence of one night, one observation per night. There we go. I apply, we resample the light curves within the LSST's photometric error. We have a bunch of error multipliers on top of that for moon phase. Seeing. I dropped 30% of all the data points just in case of weather loss or system shutdowns, etc. And also, yeah, seasonal observation. Observing camps. There we go, too. 7 months. We're working with a lot of data, and we wanted to address the big data problem with a lot of data. So yeah, I ended up with 3.6 million 5-year DDF light curves, wide uniform ranges of binary quasar properties. And yeah, I also have binaries that go in quite a few of the light curves. So I have them for both single quasars and binaries for full systems. I think as of today, it's a bit dated, I think I have 20-ish million light curves sitting on my computer. Anyone wants some of those. So we want to triage. We have a lot of data to sift through. Can we come up with some detection method fast and works well enough? It's hard to start. So we did pretty much what I told you not to do, and tell ourselves not to do, is I throw a bunch of sign fits at it and see what happens. Here are some examples. Top panel is the single isolated quasar. The bottom is the binary quasar in my data set. The top one actually looks a little periodic. It's quite interesting. Maybe a long period there. I don't know. I'd say yes. So how did it do? Oh, sorry. This is important too. I can fit almost 10,000 light curves a minute. Basic parallelization, really simple fits. Have a fast kind of triage. We can use more expensive, computationally expensive methods later. What can we do for now? Some really important work by one of my collaborators, Caitlin Witt. She used some beautiful Bayesian fits on some similar light curves as well. Her fits took 15 minutes per light curve. So my work would kind of be like a precursor to her work. I highly recommend that you check out this paper. It's quite nice. So how did those fits do? A simple sign fit can actually return the binary phase and period that we injected pretty well. Here we are showing like parameter recovery, so what we put in is what the fit returns divided by what we put in. Closer to 0, the better. And as we can see, the period and phase turned out pretty well. We get these phase folding. Nothing spectacular there. And it does a really bad job with amplitude. And that is absolutely due to the structure functions of the variability. I don't quite have time to dig into that too much. We actually didn't see too much trouble from like the damping timescale, which is cool, especially because period is quite important for gravitational researches. What about false positive rates? I guess my chi didn't really show up there, but we also checked out these are really simple sign fits. All I really have to work on for now is some like reduced chi-squareds, right? They're not Bayesian fits. We can't really compare them just yet. We need more robust methods for that. So we came up with some definition for a false positive rate and wanted to take a look at what's causing the false positive rate. And that's high high luminosity quasars, and like I said, it's because of the method that we're using. The smoother light curves result in better fits, more likely to be a false positive. Yeah, we see that here. Higher luminosity, brighter for these false positives. Some of these stars are just some current candidates that we have on our list. So binaries are hard to detect in the optical because of inherent variability. Rubin will revolutionize the field, no surprise there. Simple sign fits can recover some of the binary parameters reliably. Curve fits can also induce high rates of false positive detections, and I'll speed run this. I used uniform broad ranges of quasar properties. It's time to change that. Let's get a bit more realistic. This is next work. This is work coming soon. Using quasar luminosity functions. I'm also simulating longer baselines, all the way up to 20 years, with several different cadences. We got I used DBF for one observation tonight, and then wide fast deep, like 3, 7, 10, all corresponding to 3 observations every 3 days, 7, plus some post-galaxy contamination. Interesting results for our work with this method specifically. Baseline matters more than and yeah, we're throwing more methods at this. Really simple machine learning examples are returning some promising results here, and I don't quite have time to go through them. But thank you.
Thank you so much, Megan, for a wonderful presentation. And now, for the questions, binary sub-community application, collaboration, comments, questions, also non-binary subgroups. Yes, please.
Any chance you guys looked at the false rates?
Not in this paper, but we hope to now. And probably not in the second paper either, because those are just some minor changes to the parameter grid and then cadence baseline and just repeating what we did. Third paper, though, absolutely. That is critical. Yes, please. And I'm looking for postdocs, so if you have funding for that, no.
Yes.
I guess I have a pretty naive question, but what determines the relative variability, like range in the binary signal, the dampened walk signal?
Yeah, so the variability amplitude for the binaries is directly connected to the binary properties. Period, we're talking eccentricity. Maria has an excellent paper deriving all of those properties. So that those physical properties drive variability amplitude. And yeah, for the single quasars, definitely Eddington ratio is a big player. Yes. Yes. There should be some parameter space where it's easier to disconnect the two.
Great. Other comments? Megan is our new valuable member, please.
I've got supply curves.
Thank you. It was really nice. Is the idea that you would perform a point selection on like a color selection, or before you perform any of this? Because clearly you're not going to be doing this for literally every single object in the drilling field. You want to be selecting agent beforehand, and will that introduce biases?
I'm not completely certain, but yes, that absolutely has to be done before that. I'm assuming that we already have our AGN whittled down. Will that introduce biases? Perhaps, but I'm skeptical that it will be too harsh. It'll be too bad. I think it'll be okay. I don't know.
Thank you. And why are you focusing on just the DDFs? Is it because of the cadence? Or?
Cadence, and because I just had to start something. That was the easiest one to start with. It's a nightly cadence, so I really didn't have to do too much. And it's easy to set those arrays and whatnot.
But this could be applied to the VISTA survey.
Oh, yeah.
Oh, okay. Cool. Thanks.
Right over here. I have some of the other cadences simulated already.
Cool.
Yep. So 3 days, 7 days, a day.
Excellent. Sorry about that.
So, yeah, I had to go very quick. But yes, working on paper 2.
More questions for the person of the white.
Thank you, Megan. Really nice presentation. And I definitely would like to collaborate with you. Our group, definitely. So, fortunately, we don't have a postdoc to offer you, but we are it. So, strongly recommending to other people. So, I mean, what I think, I don't know, have you tried testing other methods to detect the periodicity in order to decrease the false positive? And you probably did. So, I really think that's a nice avenue to take and to make a synergy with other groups working as well with the LS. Yeah. Did you show the slide?
Nope, this isn't my extra slides.
Okay, thanks.
I'm trying out a bunch of other methods, including Lumsgargle periodograms and also autocorrelation function fitting as well. This is all very preliminary. There's no pre-processing I'm doing to the data currently. There are some experts in the room who I'd really like to talk to about some of this. We're trying. For now, I have the curve fits implemented and already have a paper published on that, but there's some other stuff that we definitely need to do, and I'd really like to hear you speak.
Thank you so much to Megan and to the community for empowering young people to do science.
This is really fast. My little outreach fun fact from Federico Bianco, the Rubin deputy project scientist. The Las Vegas Sphere is I guess there's internal screen. I believe she was talking about the internal screen. This is huge. If you match image and screen resolutions, you can only fit 1/100th of a Rubin image on this huge
Great. And tomorrow more about this. Thank you so much once again. And now we are proceeding to the next talk. And we are welcoming the Alistair Graham and moving a little bit further from the core of the galaxy, and we are going to galaxy morphology dependent imperial factors. So you're welcome, Alistair.
Good morning, good afternoon. Thank you. I do feel like a bit of an imposter here. I am not someone who really works on active galaxies. I work on inactive galaxies most of the time. But my collaborator in the audience, Roberto Soria, I have collaborated with him, and he's a bit of an expert on X-rays, and we may have found a few intermediate mass black holes. But most of what I'm going to talk about, it's related to inactive black holes because they can be used to calibrate virial masses for AGN. So I'm going to take you through a little bit of galaxy morphology because I believe it's quite important for understanding black hole scaling relations, which are what we need for calibrating virial factors. Okay, so I think I'll stand and look at this screen. Hopefully everybody's familiar with the tuning fork diagram. Great. So early type galaxies on the left, late type galaxies on the right, and in the middle are these lenticular galaxies, the S0s, which Reynolds introduced back in 1920, 1925. De Vaucluse modified this in many ways. One representation of his modification was he said, let's include galaxies with weak bars. So among the spirals, we've now got strong bars, no bars, and weak bars. Spitzer and Bade said, well, I think the S0 galaxies form from the collision of spiral galaxies, and the stars just pass through each other, and the gas collides and gets left behind. And that's the origin he had for the S0s. And so Sidney Vandenberg, he liked this idea, and he thought, well, if that's the case, then we're going to fade the spiral arms and eventually lose the spiral arms. And so Sidney introduced the trident in the bottom right, where it's not bar strength, it's now spiral strength, which gives you the prongs. I'm mentioning all of this because it's got to do with our understanding of the evolution of galaxies, and I think that's important for understanding black hole scaling relations. Next, I'm going to mention something which wasn't in any of the morphology schemes back then, and it is something Martha Lira introduced in 1966, and that is some galaxies, they don't have large-scale disks. They're not spirals or lenticular galaxies. There's something she called ES galaxies, E for elliptical, S for S0, something in the middle, and they've got these intermediate scale disks. This is the same galaxy, I've just changed the contrast. You can see the embedded intermediate scale disk. It's not in the classification schemes of de Vaucluse or anybody because they happened before Martha Lira discovered these. This is the same galaxy again. One of the things my group do are we model these galaxies. The data, the image is on the left, in the middle is the model, and on the right, the residual image. That's after we've subtracted away a model from the original image. And you can see we do quite a good job at capturing the galaxy that we subsequently model. One of the ways to model these galaxies is to look at the light profile on the right. That's the radial distribution of light from the center of the galaxy to the edge. It's been fit with a bulge component, Circic spheroid component, an intermediate scale disk, and a large scale disk. So we've got two disks. This galaxy is particularly interesting because it was, many years ago, heralded as a perfect example of an out of the quarter galaxy. De Vaucluse showcased this with Massimo Cappuccioli, perfect out of the quarter. And here I am telling you, well, it's not a spheroid, you got two disks in there. This is 3379. What I'm showing you here is a different galaxy, 3377, just being honest, but I've chosen this one because you can clearly see an embedded intermediate scale disk in, I need to go back. pointing the right way. Let's see, go back. The color diagrams, the top left, that's your rotation. So you can see there's a rapidly rotating disk inside a more slowly, larger scale rotating disk. So these elliptical galaxies, they're not as simple as we thought. Most of them are being reclassified as disk galaxies. Yet another example, this galaxy was alleged to have a black hole mass that was, I think, 10%, or maybe it was even 100% of the mass of the spheroid within which it resided. We went to Keck, we did a dynamical analysis. With our high spatial resolution, the black hole mass dropped by a factor of 10. With our modeling of the galaxy light, the spheroidal component is 10 times bigger. So the black hole mass, the spheroid mass ratio dropped by a factor of 100. We took a closer look at this. The original paper was a Nature paper. So, most Nature papers seem to struggle when people look more closely. Okay. Galaxies can be more complicated. I don't have time to discuss this in detail, but we look at the isotopes. If they're nice and elliptical, great, but often there's a bar in there, and that bar can wobble around, and it can create these peanut shell-shaped structures. So you've got a peanut shell-shaped structure with two pointy ends, and that's the pointy ends of the bar. So we measure all of this, we capture all of this, and when I present black hole mass scaling relations, I'm not talking about these peanut shell-shaped structures, which some people refer to as pseudo-bulges. I'm also not referring to inner disks. If it's an inner disk that's rotating, I'll call it an inner disk and I won't lump it in with the bulge. There are nuclear star clusters as well. So all those things are separated from what I'm finally going to get to. I'll skip some black hole mass scaling relations and focus on the spheroid mass, which is the true merge-built classical bulge component of galaxies. So 25 odd years ago, we thought it was a near linear relationship. You should all be hopefully familiar with this. And even today, many people still just use a near linear relationship. There's no morphology. These are predominantly early type galaxy samples. We've now got a lot more data. The spirals are in there. And there's different types of early type galaxies. Some of them are disk dominated, some of them are 2 disks. All that information can feed into these diagrams, and it's important. So all I'm doing here is showing you a basic separation of black hole mass. Let's just focus on the left, black hole mass versus spheroid mass. The blue are spiral galaxies. The spiral galaxies, they're doing something quite different to your early type galaxies. I'm now going to just focus on the early type galaxies. And just focus on the left-hand panel. I've separated early type galaxies into true elliptical galaxies, pressure-supported systems, and your lenticular galaxies with disks. So if I was to tell you, oh, I've measured the spheroid mass and it's equal to something or other for an early type galaxy, you need to ask me, well, what type of early type galaxy is it? The black hole mass that you're going to predict depends on your knowledge of the morphology of the galaxy. See, there's quite a difference there. So in the case of early type galaxies, you'd be better off not even worrying about the type of galaxy. Just use the galaxy stellar mass. They nearly overlap. On the right-hand panel, you can see that they nearly overlap. So you need to ask yourself, well, is spheroid mass really what I should be considering? Should I just look at total galaxy mass? So now, we've got 3 types of morphology. The spirals, weirdly, are in green. Again, perhaps let's focus on the left-hand panel. The spirals are in green, halfway between the ellipticals and the lenticulars. So what's going on there? Aren't lenticulars supposed to be the bridging population, unifying spirals and ellipticals? Don't you have spiral galaxies collide, pass through each other, form these? Something's not quite understood here. There's more going on, which I'll subsequently explain as we go deeper into this story of galaxy morphology. I had a look at all of the lenticular galaxies that have directly measured black hole masses, and it became apparent that many either do or don't contain a lot of dust. In the top here, it's not pointed. I can see that other people get confused here. The arrows are very clear though. Dustless, the nuclear dust disk, faint dust, which you can't really see very well, and many of the lenticular galaxies have got massive amounts of dust in them. I then went through the literature, and these dust-rich lenticular galaxies, they've always been reported to have been built by a major wet merger. So we got a collision of probably a spiral and spiral galaxy forming this class of lenticular galaxies. These, they're lower in mass, they're old, they're metal poor, they're quite distinct. Their formation history is quite distinct. So now, looking at the black hole mass, spheroid mass scaling relation, taking into account all of these morphologies, we have the red, some yellow, dust or low mass lenticular galaxies. I think they're probably primordial. They're in clusters. I think they've been around a heck of a long time from the stellar ages. They haven't evolved much. But if they weren't in a cluster where there's a hot X-ray gas cloud that ram pressure strips them, curtails their growth, so it stunts them, if they're in a more field environment, they can continue to accrete and they transition across to spiral galaxies. And if you ask someone, how do you build a spiral galaxy? Well, they'll say, well, you start with a disk, then you have a perturbation, accrete material, perturbate. You develop a spiral pattern in what was a spiralless galaxy. If you then collide those spiral galaxies, you form your dust-rich lenticulars, which are in green. If the dust-rich lenticulars then undergo a merger, that's when you start to build the Martha Lilla's ES galaxies with not the large-scale disk, a smaller disk. Spiral-spiral collision, you've got a lot of angular momentum, so you can't immediately build an elliptical galaxy. You end up building lenticular. Lenticulars, less angular momentum, bigger bulges. If they collide, then you jump across to your ellipticals, which is shown by the red line. And then the BCG is the dashed line. So there's this transition. And so again, if someone says to you, I've got a spheroid mass, tell me what the black hole mass is. Well, if you're just using a single linear relation, you're missing all of this. If you additionally know the morphology, you can predict a much more accurate black hole mass. That's 3 minutes. I think I can do it. I'll have to quickly go through this because I'm running out of time. But on the left, you do see those transitions I was talking about, how accretion builds up spirals from lenticulars, mergers, whatnot. That then maps into what you see on the right, which is your early type galaxies forming a sequence that connects with your S0s down here. So this is low mass down here, high mass up here. This is your early type sequence. But you might have the early type galaxy become a spiral, or it might merge to become an elliptical. And then these dust-rich lenticulars, they can merge to become ellipticals. So what I just described is shown on the right. It's an evolutionary sequence. It compares with the trident on the left, but this is the Atlas comb. It's very similar to the Vandenberg trident. What was missing from all of our morphology schemes in the past, tuning fork, trident, comb, it wasn't really an evolutionary sequence. It was a morphology gradual shift sequence. For example, with the comb, if you're looking at the spiral galaxies, their only hope to evolve anywhere in this diagram is down to become a weak spiral. There's no, well, what about major mergers? None of that had been captured in our morphology evolution schemes before. But now we'll capture in the triangle. Quickly, if you were thinking, well, you mentioned that you could just use galaxy mass, galaxy stellar mass. Okay, well, this is galaxy stellar mass here for the different types. The blue are the spirals. They've got a slope of 3 in this diagram. Your major merger built galaxies, your lenticulars built from a major wet merger, your ellipticals built from major dry mergers, they tend to follow a relationship of 2. And then your low mass lenticular galaxies, they're completely offset. So if someone says, I've got the galaxy stellar mass, what's the black hole mass? And you're just using a single linear relation, you can do much better. If you know the morphology, you can do a lot better. That all becomes important. Similarly, in the M sigma diagram, there's subdivision, there's demographics. All I showed you was black spheroid mass. the other scaling diagrams, they've also got this morphology importance that's been missed. And why does it all matter? This is my final slide. Why does everything I say matter? Well, it's because, and this is where I first had my connection with the active galaxy community, I had the black hole mass velocity dispersion relation years ago from my work, and I was able to use it to calibrate what the virial F factor is for bringing virial AGN masses in line with black hole masses. If you want to know the black hole mass from the virial AGN mass, you need this virial F factor. And the F factor F, it simply shifts all of those black data points, which are AGN, into agreement with the relation we observe for active galaxies. There was no consideration of galaxy morphology in this diagram. It's dominated by early type galaxies. I would like to revisit this, obtain F factors for different galaxy morphologies. I can use this diagram, black hole mass velocity dispersion. I can use black hole mass spheroid mass. I can use black hole mass galaxy stellar mass. Maybe the F factors will all be the same for different morphologies. Maybe they will be different. Maybe elliptical galaxies, which are dust poor, maybe there's something different. The dust-rich lenticulars, maybe we're going to find offsets. So I hope to be able to provide better virial F factors, which go into the calibration that we use for obtaining AGN masses. I know I ran a little over time. Thank you for allowing that.
Thank you, Alistair, for great talk and questions.
Thank you very much. Very interesting. I would like to know more about how you compute the black hole mass and the stellar mass, because I think that make also a difference in your results.
Well, I presume you're referring to the inactive sample.
Your plot when you're using stellar masses and black hole mass, what are you using for this quantity?
So for the black hole masses, they've predominantly come from the literature. There's only been a couple of galaxies for which I've gone out and directly measured the black hole mass. So coming from the literature, it's Keplerian, it's spatially resolved dynamics around the black hole. The uncertainty on the black hole masses are typically less than a factor of 2. So there's not much wiggle room typically, although I did just give an example where one galaxy is strong by a factor of 10. The stellar masses are quite simple. You obtain the galaxy light, you decompose it into the different components. You then have a fraction of the light in the spheroidal component. You then need a stellar mass to light ratio to convert. Yeah, I use color dependent stellar mass to light ratios. Well, it's a color dependent. So your blue color is matched to your spirals. So you will have a different mass to light ratio because your spirals are bluer. And if you've got a red color, then the mass to light ratio is different. It's matched to the elliptical. So yes. Yeah. Yeah, I don't expect much change because I work with 3.6 micron data, and at 3.6 micron, the variation in the stellar mass to light ratio is small. If I was obtaining luminosities in, say, the B band, you can have factor of 2, factor of 3, maybe uncertainty in stellar mass to light ratio. But 3.6 micron with bits of data, there's very little wiggle room in the, I could have the color wrong by a lot for dust reasons, although I do create the dust, but the stellar mass to light ratio is not going to change much. So those relations that I showed for different morphologies, that's pretty solid. There's not much scope in the inputs that's shifting around.
Yes, here. In your triangle sequence, evolutionary sequence, you say that lenticulars precede spiral galaxies.
Low mass lenticulars, yes.
Low mass lenticulars. Are enough of those out there to kind of provide for, because we know that spirals are found in low density environments. And my understanding is that lenticulars are normally seen in high density environments. So what are those, the primeval dust poor S0s?
In clusters are full of what we used to call dwarf ellipticals. I don't think I have the answer for that. You're thinking, okay, Spitzer and Bade, they introduced this idea that S0s are faded spirals, and they were wrong. They thought, okay, you collide them together.
More than that, it's just how they are distributed in large scale structure. S0s, I understand, they're mostly found in clusters of galaxies. So where are the S0s in the field that should be converted into spirals, which is the preferred place where you find spirals? In the field, or more like in low density environments like groups and stuff like that?
Yeah, no, I think they're forming clusters, but I don't know why. We should talk later.
Thank you. Thank you so much once again. And thank you to the community for the great interaction. Now we Rousseau, related to probing AGN dynamics through natural language process. Welcome, Luke.
Okay. Your pointer? Right. Thank you. Just to check, yeah, that is the pointer. That's forward, that's back. Good. Okay, I'm sorry you're going late to lunch. Don't associate with my talk. Okay, so my name's Ben. I'm a PhD student at PUC in Chile, Universidad Católica, working with Bauer and my co-supervisor Guillermo Cabrera. I want to say thanks to the organizers for putting my talk on. And yeah, I want to present the start of my thesis, which is looking at AGN dynamics using natural language processing. So, as a really brief intro to, stand up here, to getting black hole masses from type 1 spectra, the majority of the time, what we do is we get a full width half maximum from a broad line, we combine it with the luminosity in the continuum near that broad line, and we get the mass for that specific broad line. And we can do that for H beta, magnesium 2, and carbon 4, and some other lines. But when we look at how each of the masses look against one another, we notice that for things like magnesium 2 and H beta, which are low ionization lines, the masses that we can extract from them follow the one-to-one with a bit of error. And when we look at carbon 4, which is a high ionization line, which is closer in to the black hole, we see that this correlates so well with the low ionization line masses. So this is potentially because there are outflows in carbon 4 line, so we get absorption features, and those are the Bowel QSOs that we see. So about 40% of sources are predicted to have these Bowel features. So that's why we just don't see this correlation in the mass. And we also see that when we look at the single epoch mass compared with the reverberation mass, we see a fair amount of scatter, especially in carbon 4. So the issue they all have is that they focus on one broad line. And we know from previous works for over 30 years that there is correlations in the AGN spectrum. So, for example, the eigenvector 1, where we look at the correlation of oxygen 3 beta to the anti-correlation, the fourth half ion 2. And this is theorized to be due to the orientation of the AGN. So what we ask is whether we can leverage information from all of the spectrum of the AGN to get a better understanding of black hole mass. So to do that, we use the transformer plus attention machine learning. We had a little bit about the attention yesterday, but I want to talk about the transformer mechanism, which is presented in a paper called Attention is All You Need, that was finally in 2017. And as a point, yeah, this is what ChatGPT is the mechanism used to train ChatGPT. And I don't want to go too much into the architecture, but I think the attention mechanism is really important because I'm going to bring up this plot a lot. Basically, the attention mechanism, so it was originally designed to take in language, translate it, so French, take in English, and then translate it into the English. So this will be in training. And what the attention mechanism does, is it basically creates a connection and learns the relevance between every single point in the input sequence. And that also happens in the English sequence as well. So we get a connection to every single point. Then we go into this attention matrix in the middle, this cross attention matrix, and it creates a connection between every single input in both sequences to output. And basically what the attention does is it creates probabilities to show us which part of the sentence is more relevant or least relevant for, in this case, translation. So just to quickly show, so we'd have this label set, we'd have French, we'd have English, and we get English, and this is in training. And then in testing, you remove the English, you give it French, and then you take out English. So we wanted to input AGN spectra into this transformer to try and do a similar, similar method. So basically, we initially wanted to put in the AGN spectra as the French, and then as the English, put in things like black hole masses and pretty much any other information you can extract from that spectrum to then output black hole mass. So that when we go into testing, we just have the spectrum, we get these values. However, as I pointed out at the start, there are some uncertainties in the single epoch masses. So if we input the single epoch masses into the English section, we're just going to learn the equations that govern these masses. So we want to use a slightly different method to understand if the transformer can actually extract more information about the black hole mass from the whole spectrum. So what we chose to do was decide if we could, put in the AGN continuum as the French, so hiding or masking all of the broad lines, putting in the broad lines, therefore masking all the continuum as the English. Pass it through, it learns all of the connections and relevance between each of the points, each of the flux values, to then output broad lines. So in testing, we just give it this continuum, we get the broad lines. And if it can give us these broad lines, we know that it's understanding some information in the continuum about the black hole mass. So, a quick word on the training set. So we're using SSSDR16Q, which has about 700,000 QSO spectra. We're using most of it actually. So, and we're splitting it into three different samples. So the first one, we're looking at the optical broad lines, including magnesium-2. So what we do is we mask magnesium-2, H gamma, H beta, and the oxygen 3 lines, and H alpha, and just give it a test and see if it can predict that. Then we also look at UV broad lines. Mainly here, we are masking all the broad lines, but we're masking carbon-4 to see if it can predict carbon-4, but also if it can reconstruct that broad line in the face of BAL QSO. And finally, which I'll really briefly touch on, is the Lyman alpha. So we basically mask anything bluewood of 13 times and try and predict the Lyman alpha, which would be really good at high redshift. Here are some results for the optical broad lines. So here I'm showing a test set of 4,000 spectra. So we've trained on all of the spectra. Now we're looking at just this test spectra, 4,000 spectra. And we're looking at the median predicted over true fluxes. And we see, for the majority of the time, the median ratio follows this one-to-one line, or the zero error line. And when we plot the one sigma distribution, we have about 20% error. Apart from in H alpha, where we see a lot more error, but that's mainly due to the fact that only 30–40% of our spectra are fully covered in H alpha. So we kind of expect that. And then we had a look at why some sources might have more error. And so here we're plotting this median predicted true flux against the signal to noise of the spectra. And we see that pretty much anything below signal to noise of 5 has a lot of error in the fluxes, but then above that, we're following up with one line. So then going on to the UV broadline results. So again, showing oxygen 1, silicon, and then carbon 4, and carbon 3, we see that the median ratio follows one line. And here we've got some examples of BAL QSOs. We have absorption, heavy absorption in carbon 4. And being given the red part of this spectrum, the algorithm is able to, or the machine learning method is able to predict the carbon 4 and reconstruct that carbon 4 line. And when we look at the errors in carbon 4, we see that there is like a 40% over prediction, but we don't see it in the under prediction. So it's because of the bulk QSOs being in our sample. So then the attention mechanism. So the attention plots what it gives us probabilities. And the probabilities kind of show us where it's looking in the continuum spectrum to do its predictions, to predict the broad lines. And each attention block has 4 heads. And these can be thought as principal components. And we see when we plot the attention probability spectrum from each of these heads, we see that in the first 3, it's mainly looking in the ion 2 continuum, looking at some individual ion lines. And then when we look at head 3 and 4, looking around the Balmer continuum, it's looking at helium 1, neon 5 as well. So we get an idea of where it's looking in the continuum spectrum to predict broad lines and maybe later on predict the black hole maps. And then really quick preliminary results, we see we put this into the algorithm to predict the Lyman alpha, which is doing quite well. Again, 4,000 test spectrum, we look at the median spectra that predicted over true. Obviously, we see a lot more error. Blue wood of the Lyman alpha line because of the absorption that we see at high rate. We also are able to input the left-hand side of this spectrum to predict the right-hand side. We see that it's predicting well the option 3 lines, it predicts well H alpha, even in when there's lots of noise. So, how does this have potential for LSST? So here are 2 works also using the transformer mechanism. Here in Donoso Olivia in 23, they use microclassification and also reconstructing magnitudes by putting in the time of the observation of a light curve and the magnitudes. They're able to reconstruct magnitudes, do some light curve classification. Also in 2024, in AstroClip, they input spectra and images into this encoder and this shared embedding space to do some classification. So we also want to go multimodal. And there are a couple of things that we've envisioned with this. And one is going back to the French and the English. What if we were able to put in a light curve from an AGN as the French, and then spectrum corresponding to that light curve as the English, and then when we remove the spectrum, we could predict things like the black hole mass that we've learned from the spectrum and any learnable parameters that you want. Or we could also think about removing the spectrum and trying to predict a spectrum from the light curve, but that's a bit more unlikely, I think. Then we look at reverberation mapping analysis. So again, we could think about inputting the continuum flux as the French and a broadline flux as the English. And we can either improve lag detection, hopefully, or we can think about predicting this broadline flux from the algorithm. So if we don't have the broadline flux, we can put in the continuum flux and get that. Thank you. Get that broadline flux from there. So yeah, this is all in the working, hopefully coming in the future. These are just ideas of what we could possibly do with this algorithm. And then finally, we could look at putting in 2 or both of the light curves from reverberation mapping and the spectrum, and maybe try and predict spectra from the reverberation mapping light curve. And yeah, I was quicker than I thought it'd be, so you can go to lunch earlier. And I'll leave my summary there. Thank you.
Yes, this is super promising. So one question about the low luminosity AGNs. Do you have sources dominated by the host component? And how are you able to recover them?
At the moment, we're just using SSQ.
So very bright sources.
Yeah, yeah.
Well, I guess there are a few with host dominated. I remember it was Racksheet that was providing the fraction of the AGN contribution. I don't know if you catalog it's also included, but it would be nice to see, because if you can also recover the host component, even for bright quasars, you're solving a huge problem.
Yeah, right.
Also, how did you select the training sample? because your prediction of the lines is amazing, and I wonder whether you cover the full sequence of possible profiles and strengths of the lines and things like that.
Yeah, well, I don't have anything to show actually, but we're just taking a redshift cut on the 16Q sample and putting in everything and randomly splitting it into the algorithm.
Probably you want to, what's it called? When you normalize things so that everything is represented equally. Yeah, it looks like an imbalanced sample then. So it's gonna do a wonderful job with just kind of your average quasar, but for objects which are a bit different, and we want to understand why.
Yeah.
Maybe it's gonna get completely.
But then the bulkier cells are fairly different, and it's able to reconstruct the carbon-4 when there is absorption.
If they are in your sample, in your training sample, and well represented, you should be fine.
Yeah.
So a suggestion regarding that, in our paper of 2021 for the anomaly detection, we had the same problem, and we just created a training set that was normalized in terms of the physical properties. And solved the problem.
Yeah, great.
Here we have the question, the last question. Okay. Okay. So thank you to all speakers and to the community for great interaction. Have a nice lunch.